Mm-hmm. Mm-mm-mm. Okay, so we were watching this guy. Let's go back. Wait, we need to see that the audio is good. You is live. Very nice, very nice. Mm-hmm. She's my idol. You is live. Very nice, very nice. Let's see. Anyway, I want to watch this guy. I want to see everything he's got. Let me see. Let me see more stuff that he has. I'm gonna get a drink of the Vasa. The Vasa. hmm Why wave function? Hmm. Very interesting. Hmm.
Quantum mechanics has a bit of a reputation for being incredibly counterintuitive and also mathematically very challenging. I can't argue with the counterintuitive part. As we'll discuss in a minute, the way tiny things like electrons behave is undeniably strange compared to our everyday experience. But I think the second part about the math being super complicated is a little bit unfair. And by the end of this video, I hope you'll agree that the basic mathematical object of quantum mechanics, the wave function, is actually fairly simple. But let's back up a step. When you start out studying physics, you learn about the motion of things like baseballs and pendulums and even planets. All that falls into the category of classical mechanics. And our basic job in classical mechanics is to figure out the position of a particle as a function of time. Or in other words, its trajectory, x of t. About 100 years ago, though, people discovered that the physics of tiny objects, like atoms and protons and electrons, is very different. They're instead described by quantum mechanics. And quantum mechanical particles hardly behave at all the same as
I don't understand why they keep saying particles after they've already concluded that there's only waves. I don't know why they keep repeating this. So the conclusion was it's all waves. Let's continue saying particles and let's become confused. So I don't understand them. Just say waves and deal with the waves. Just figure out these waves. There is no particles. So stop saying particles. You say there are no particles, then stop saying particles. Jesus.
classical objects like baseballs. For example, we'll discover in a few minutes that a particle like an electron doesn't follow a single well-defined trajectory when it travels between 2 points. Instead, it's described by a wave function, psi, which is a function that's spread out through space and which tells us the probability of where we'd find the particle when we go to measure it. We'll see in this video how that language of wave functions comes about by investigating a very simple setup called the double slit experiment. You might have heard about it before. It's pretty famous as physics experiments go. The idea is basically to throw different things at a wall with two little holes cut into it and see what comes out on the other side. What we find will depend on whether we were throwing classical particles, classical waves, or quantum particles. And what we'll discover is that the quantum case exhibits a sort of mixture of the properties of classical particles and waves. That's what textbooks sometimes give the fancy name wave particle duality. But we'll see how the consequences of this experiment lead us to the idea of the wave function. And like I said, the math that's involved won't be too complicated. Going into this video, the most advanced math you'll need is really just to know a bit about complex numbers. What's challenging is the conceptual idea of describing a quantum particle by this abstract function psi, when again, in classical mechanics, we'd simply write down its trajectory. You might wonder if there's a different way of approaching quantum mechanics that still describes things in terms of regular old particle trajectories, as opposed to this more abstract language of wave functions. In fact, there is. It's called the path integral formulation of quantum mechanics, and it was invented by Richard Feynman, whom I quoted at the start of the video, a couple of decades after Schrödinger and friends first worked out the wave function approach. The catch is, instead of following a single trajectory like in classical mechanics, a quantum particle does a kind of statistical average of every trajectory it could conceivably take between 2 points. But more on that later. This video is actually the first of a series of lessons I want to share with you, explaining Feynman's way of looking at quantum mechanics, because it can give you an incredibly powerful intuition for understanding the way physics works at microscopic scales. And you can subscribe if you want to make sure you see those follow-up videos. For now, though, we need to start with the basics and uncover how all this weirdness with probabilities and wave-particle duality comes about when we study the behavior of really tiny things. So here again is the setup of the double slit experiment. We take this solid wall.
Hey, what's up? Oh, spaghetti. Hey, what's up?
Hello, I'm fine, thank you. And you?
Fantastic. Did you read the papers that I sent you?
Not yet.
Okay.
I'll read them when I get around to it.
No, it's no issue. I mean, you can ask me. I mean, these are papers that I wrote. I just started writing them. Yeah, I need to finish them, obviously, but I mean, it's just an interpretation of modern physics. I'm not disagreeing with SR, GR, QFT. I'm not disagreeing with anything. I'm just reinterpreting everything through the ether, and everything
All right.
becomes super simple. Everything becomes really straightforward. Everything works together, and I can easily make predictions about the universe and about quantum physics and about SR and GR. I can easily understand it. A child, yeah. Anyway, do you want to talk about something?
Okay, so how do you explain quantum?
So quantum comes out of understanding ether. So everything started for me when I was reviewing Veritasium's video called "Something Strange Happens When You Follow Einstein's Math." So he was talking about black holes. So I took out a piece of paper and I wrote F equals ma and F equals gmm over r squared, and then F equals F. So ma equals gmm over r squared. The m's drop out, and what you see is that you have a vector field equation of gravitational acceleration according to Newton. A is a vector. A equals gm over r squared. That's a vector. What?
Yeah.
So that's a vector field equation that basically says that everything in the universe, right? Let's start with a point mass at the center of the universe, and let's place a test mass at infinity. So it's experiencing acceleration is equal to gm over r squared. So it's slowly going to accelerate whether it has mass or not. So even light now is bending. So from Newton we can already see that light is bending. Any particle, regardless of whether it has mass or not, is now accelerating towards this point mass. Even things that are massless. Okay, so everything, so test particles anywhere seem to accelerate towards this point mass, and I derived from this acceleration vector field equation of gravitational acceleration, I derived from it a velocity field equation, meaning something has a velocity. I don't know what that is, but something everywhere in the universe where there is a single point mass in this universe, something has a velocity. Something has a velocity. Something is flowing into this point mass. I don't know what that is. Anyway, so then I was thinking, why does the apple accelerate towards the ground. And what seems to be is that there is something flowing into the earth, or into the point mass, or into the earth. There's something flowing, and it's going through, it's dragging the apple with it, and it's dragging me into it. Everything is being dragged into this mass, into earth. So I was thinking, okay, but why can't I feel this thing? And how, right? So I'm sitting here, and there's something flowing through me, and that is why I'm being dragged towards the ground. But I couldn't figure it out. Why can't I feel it? Why can't I feel this fluid? And my conclusion, my intuition was, it must be that I'm waving through this fluid, just like QFT says. QFT says everything, right? Everything is waving. Everything is waving. So that gives me the prediction of the particle wave duality. So already, just from starting from, this is from Kepler, from Tycho Brahe, we have Kepler. From that we have Newton, and from that we understand how an apple falls. And from this now, we can already see the particle wave duality, that what seems like a particle cannot be a particle, because otherwise it would experience friction. Everything would heat up as this fluid is flowing through me. I would heat up, but I'm not heating up. The only way I'm not heating up is because, in my intuition, is because I'm waving through it. Well, that makes sense. That's why everything is a wave. Now, once you assume that there is this fluid, then immediately you get a constant speed of light. Immediately you get, from this fluid, from this ether, you get the luminiferous ether, that version of the ether that everyone believed in until Einstein. And that's the ether that allows light to propagate through it as a wave. And that's how you get a constant. Immediately you get the second postulate, Einstein's second postulate from 1905, the theory of relativity. He just postulated speed of light as a constant without any reason. That's just a given. That's just, that's what we discovered, he said, basically. We are unable to find the ether, so let's just assume a constant speed of light. I don't need to assume a constant speed of light. I can derive a constant speed of light because there is ether. Then the question becomes, then why is the speed of light a constant? Why is everyone measuring the speed of light a constant? But that's very simple. Einstein already explained that. That's because our brains are light based. We are all composed of waves that are waving at the speed of light. Everything inside us, every mechanism, every clock we will ever use, ultimately is based on these waves, on the ether. It tick-tocks through the ether. Every clock we will ever come up with is based on the ether, is waving through the ether. So that's the first paper that I showed you that proves Einstein's second postulate. If your clock is based...
Very cool. I have to leave now. Bye.
Okay. Oh my God, this is the only person I can talk to about this topic. Well, him and Cenas. Well, at least it's recorded. Anyway, let's continue. We were watching this. What were we doing? I don't remember before he came in. Oh, I opened a different browser. For some reason, I opened a different browser. Let's, yeah, we were watching this. I was chewing gum and kicking ass, but I'm all out of gum. So I'm all out of bubble gum. Does anyone know this? That meme? And I'm all out of bubble gum. Here, you need to know this. And I'm all out of bubble gum. La 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 la. And I'm all out of bubble gum. Ta na na na.
I have come here to chew bubblegum and kick ass. And I'm all out of bubblegum.
Oh my god. La 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 la. La 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 la. I can watch memes from dawn to dusk. La 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 la. La 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 la. Destruction of the state of Israel. Da la la la. Anyway, that was that meme. Anyway, so we were watching the double slit experiment. So if we listen to what he said, everything he said is like you're talking about you're always showing particles and always complaining nothing makes any sense. I think I can safely say that nobody understands quantum mechanics. Richard,
Quantum mechanics has a bit of a reputation for being incredibly counterintuitive and also mathematically very challenging. I can't argue with the counterintuitive part. As we'll discuss in a minute, the way tiny things like electrons behave is undeniably strange compared to our everyday experience. But I think the second part about the math being super complicated is a little bit unfair. And by the end of this video, I hope you'll agree that the basic mathematical object of quantum mechanics, the wave function, is actually fairly simple. But let's...
Okay. I mean, the wave function is because de Broglie said everything is a wave. Einstein said light is not just a wave, it's also a particle. I don't know about that. It's a finite wave. I don't know if it's a particle, because even light as a wave has momentum. We've saw that lecture. That light has momentum. So it doesn't need to be a particle. It has momentum. It doesn't need to be a particle. It's a wave that has momentum. It's a wave that has momentum. It's not a normal wave. It's not an ocean wave that just goes through a ship, let's say. It cannot, it doesn't move anything. It's a different type of wave. It's not a normal water wave. It's not a sound wave. It's an electromagnetic wave. It interacts with things electrically and magnetically. And between those two things, it actually pushes them. It actually behaves not as if it has momentum, it actually displays momentum. So you don't need to say it's a particle. It has no mass, but you don't need to say that it has you don't have, anyway, I don't know. Anyway, let's listen.
Let's back up a step. When you start out studying physics, you learn about the motion of things like baseballs and pendulums and even planets. All that falls into the category of classical mechanics. And our basic job in classical mechanics is to figure out the position of a particle as a function of time, or in other words, its trajectory, x of t. About 100 years ago, though, people discovered that the physics of tiny objects, like atoms and protons and electrons, is very different. They are instead described by quantum mechanics, and quantum mechanical particles hardly behave at all the same as classical objects like baseballs. For example, we'll discover in a few minutes that a particle like an electron doesn't follow a single well-defined trajectory when it travels between 2 points. Instead, it's described by a wave function, psi. which is a function that's spread out through space and which tells us the probability of where we find the particle when we go to measure it. We'll see in this video how that language of wave functions comes about by investigating a very simple setup called the double slit experiment. You might have heard about it before. It's pretty famous as physics experiments go. The idea is basically to throw different
See, he's showing. Oh, this is classical. Oh, okay. Classical, yeah. You're firing balls. Okay.
things at a wall with two little holes cut into it and see what comes out on the other
Classical
side.
waves.
What we find will depend on whether
Classical waves. Okay.
we're showing classical particles, classical waves, or quantum particles. And what we'll discover is that the quantum case exhibits a sort of mixture of the properties of classical particles and waves. That's what textbook.
So this is quantum. Why do you say particle? That's just a detection. I wouldn't say it's a particle. I mean, we know that the electron is very big when it travels, but then it attaches itself to an atom and it becomes super, super tiny. But even then, it's a wave. Even as it attaches itself to an atom, it's a wave. It's always a wave. Sometimes it's a big wave, sometimes it's a tiny wave, but it's always a wave. I wouldn't say it's ever a particle. When do you ever see that it's a particle?
Books sometimes give the fancy name wave-particle duality, but we'll see how the consequences of this experiment lead us to the idea of the wave function. And like I said, the math that's involved won't be too complicated. Going into this video, the most advanced math you'll need is really just to know a bit about complex numbers. What's challenging is the conceptual idea of describing a quantum particle by this abstract function psi. When again, in classical mechanics, we'd simply
Why do you say that it's an abstract function? Why do we have an abstract function? Why not have a normal function?
write down its trajectory. You might wonder if there's a different way of approaching quantum mechanics that still describes things in terms of regular old particle trajectories, as opposed to this more abstract language of wave functions. In fact, there is. It's called the path integral formulation of quantum mechanics.
But what if it's a wave? I mean, if it's a wave, then the wave function is, or an actual wave, not an abstract wave, but an actual wave function should describe it better than anything else. The path integral formulation, I would say, has nothing to do with it because it's not a particle.
And it was invented by Richard Feynman, whom I quoted at the start of the video, a couple of decades after Schrodinger and friends first worked out the wave function approach. The catch is, instead of following a single trajectory like in classical mechanics, a quantum particle does a kind of statistical average of every trajectory it could conceivably take between 2 points. But more on that later. This video is actually the first of a series of lessons I want to share with you, explaining Feynman's way of looking at quantum mechanics, because it can give you an incredibly powerful intuition for understanding the way physics works at microscopic scales. And you can subscribe if you want to make sure you see those follow-up videos. For now, though, we need to start with the basics and uncover how all this weirdness with probabilities and wave-particle duality comes about when we study the behavior of really tiny things. So here again is the setup of the double slit experiment. We take this solid wall and cut 2 little holes or slits in it. We're going to chuck different things at the wall and see what comes out on the other side. And believe it or not, this simple setup is going to motivate where the idea of the wave function comes from. Let's start with classical particles. So we're going to forget all about quantum mechanics and just suppose that we shoot something like BB gun pellets at the wall. A lot of the pellets will hit the wall and bounce backwards, but some of them will get through one hole or the other. Let's keep track of where they end up by putting a backstop behind the barrier. It's made of clay or something, so that when the pellets hit it, they get stuck. And that way we can count how many hit and where. If we only have the left hole open and the right one is closed up, and we make a histogram recording where each of the pellets hits the backstop, we expect to get a distribution that looks something like this, with most of the pellets hitting in the region behind the left hole. Likewise, if we close up the left hole and only open up the right one, we'd see something like this, with the pellets clustered on the right. And of course, when we open up both holes, the total distribution will look like the sum of those 2 individual distributions, because each pellet either goes through one hole or the other. There's nothing mysterious going on here so far. We're just talking about the regular old classical motion of these little pellets. But now let's suppose that instead of firing BBs at the wall, we send in waves instead. For example, say we shine a laser beam at the barrier, with the holes resized appropriately, of course. We're still in the realm of classical physics here, but this is a more interesting problem now, because the waves coming out of the 2 holes will interfere with one another and produce what's called an interference or diffraction pattern on the back screen. And really, these could be any kind of waves, by the way. You could even think about water waves rippling on the surface of a pond. On the other hand, it might actually be harder to try to picture things in 3D, so I'll mainly stick to this 2D picture using the laser light example. If we close up the right hole again and look at the intent.
But they never tested it with a hole. They always tested with a slit. You even called it a slit. Now you're calling it a hole. I don't think there was ever an experiment with a hole conducted. Wait, this is from a year ago? So he said he's going to make more videos, but he never did. You, the king of physics education, has returned. Anyway.
Intensity of the outgoing light on.
Wait, let me see. The audio is good. The audio seems to be fine.
On this observation screen, the shape will look fairly similar to what we drew a second ago for the BB pellets. And correspondingly, when you look at the screen, you'll see a band of light with that profile. Let's call that I1, the intensity of the light with only hole 1 open. Likewise, if we close up that hole and open up the other one, we'll get a similar pattern I2 that's shifted over slightly behind hole number 2. There are 2 key differences here compared to the BB pellets, though. First, there's the obvious difference. The BBs were discrete particles. Each of them hit the backstop as individual lumps. The laser light, by contrast, is a wave, classically anyway. It's a continuous distribution of energy and momentum. The second key difference comes when we open both holes.
But what is a laser? A laser. What is a laser? So I finally learned what a laser is. Okay, it's basically light, I guess.
Holes. If light behaved like the BB pellets, we could just add together the 2 curves here to find the total intensity we should get with both holes open. If that were true, the image on the back wall would look something like this, with a wide band of light. But that's not what you'll see when you shine a laser beam on a pair of narrow slits. Instead, you'll see an image like this, with many little fringes of light separated by intervals of near total darkness. And that's what we call an interference pattern. The corresponding intensity curve with both holes open would look something like this, with many alternating peaks and valleys corresponding to the bright and dark spots on the screen. Clearly, it's not simply the sum of the intensities I1 and I2 that we had when the individual holes were open. We call it an interference pattern because it arises from the 2 waves emanating from the holes interfering with one another. The bright spots appear where the waves interfere constructively, which just means that they've added together to make a bigger wave. And the dark spots are where the interference is destructive, and the 2 waves have canceled each other out. The physics going on here is absolutely fascinating. Think about it. With just one hole open, there was plenty of brightness all throughout the middle of the screen, like at this point, for example. But by opening up a second hole in the barrier and letting more light through, a spot like this that was bright now winds up darker than it was when only one hole was open. It's kind of mind-bending, and we haven't even gotten to the quantum mechanics yet. Indeed, the reason we're talking about all this right now is that we're about to see a very similar interference phenomenon in quantum mechanics that's closely tied to the idea of the quantum wave function. And so before we get there, it's important that we take a couple of minutes to understand how the interference pattern comes about for classical waves. To keep things simple, we'll suppose that the gaps in the barrier are very narrow. That way, after the incoming plane wave strikes the barrier, it breaks up into 2 spherical waves, psi1 and psi2. Then, those spherical waves travel along until we intercept them far away on this observation screen. But crucially, because the holes in the barrier are separated a little bit apart, the profiles of those 2 outgoing waves will be slightly offset from each other. The total wave is the sum of the 2 contributions. Where the 2 pieces have the same sign, like right here in the middle, they add together constructively and make a bigger wave. On the other hand, when they have opposite signs, the waves cancel each other out destructively. And that's the basic origin of the bright and dark spots we observe on the screen. But let's try to actually make that precise with some equations. We can write the incoming wave as some amplitude a times the cosine of an angle phi, where phi is a function of the vertical coordinate y and the time t, given by 2 pi over lambda times y minus vt. This is the standard sort of form for a wave that's traveling along in the y direction at speed v. If we draw it at a fixed instant in time, lambda is telling us how far.
I was going to say y is up, but now he's drawing y to the right. But fine, okay.
Apart the successive peaks are, and A tells us how tall they are. In the case of light, those would correspond to the color and brightness of the laser. Of course, a light wave is actually built up of electric and magnetic fields, which are vectors, but it's enough to think about a simple scalar wave like this to illustrate the origin of the interference pattern. And actually, if you've studied waves at all before, you might know that it can quickly become a bit of a pain to write things in terms of cosines like this. It's much more convenient to write down a complex wave, e to the I times phi. The idea here is
So even a water wave is abstract, has I in it.
that we're using Euler's identity, which says that e to the I times something is equal to the cosine of the thing plus I times the sine of the thing. And so we can think of our original cosine wave as the real part of this complex wave. But exponentials like this are much more convenient to work with than cosines. So this is a useful trick.
So we always use the real part. We always ignore the complex part, the imaginary part.
Dealing with classical waves. And it'll be essential when we go to write down the quantum mechanical wave function in a minute. Meanwhile, on the opposite side of the barrier, we can write the outgoing waves in a similar way. But because those are spherical waves, they don't just vary with the vertical coordinate y anymore, but instead with the radial distance from each hole. So if we write r1 for the distance from the first hole, then psi1 will be proportional to a times e to the I phi of r1 and t. And likewise, we'll put r2 for the distance from the second hole, so that corresponding wave is e to the I times phi of r2. The total outgoing wave is given.
What he means to say is that these are radial waves. So the function, namely the amplitude, is a function of the radius, not even the vector radius, just the radius. So the distance, let's say take half the arrow here. Now draw a semicircle like over here. It's the same amplitude. This radial is this all the same amplitude.
By the sum of those 2 contributions. Finally, the thing we're actually looking for is the intensity of the outgoing wave, which is what tells us how much energy is hitting the observation screen on average. That should be a real number, of course, so we'll need to take the absolute value of our complex wave. And in fact, the intensity is given by the square of the absolute value. I'll show you how to compute that in the notes that I wrote up to go along with this video. You can get those for free at the link down in the description, and I go into more detail there about a lot of what we're learning here. The algebra isn't too important right now, though. The point is, when we plug in our 2 spherical waves, we obtain the intensity curve that describes the interference pattern of alternating bright and dark fringes. So the main thing I want you to take away from all this is, again, that we obtained the total intensity by adding together the complex phases emanating from each hole, and then taking the modulus of that squared. One last thing about these classical waves before we switch to the quantum case. There were 2 terms in the sum here because we assumed that each hole in the barrier was really tiny, so that one spherical wave emerged from each. In reality, of course, the gaps will have some finite width to them, and that's what's responsible for the more intricate interference pattern I showed you a minute ago. But we can also understand the interference for wire slits, or for any shaped gap in the barrier, using essentially the same strategy as we've done here. Because whatever shape you want to punch out of the wall, we can build it up by starting with a solid barrier and drilling out lots of little holes like we've been talking about here. Then each little hole is a source for a spherical wave that propagates outward toward the detector. And to understand the interference pattern, all we need to do is add up the complex phases from all those individual waves. The slick part of the argument is that eventually we'll have drilled out so many little holes that that whole region of the barrier has disappeared entirely and left us with the shape we wanted. That's the idea behind what's called Huygens principle. And we'll come back to a very similar argument in the next video when we talk about Feynman's path integral approach to quantum mechanics. But okay, that gives us enough of an idea of how things work with classical waves. Now it's time to see how all this connects to quantum mechanics, which is where things are going to start to get a little strange, to say the least. Let's run this.
So this was just water? This entire discussion was water? So now I'm confused. Now I'm confused. I need to study the wave equation, the abstract form, the complex form of the wave equation.
Of course, a light wave is actually built up of electric and magnetic fields, which are vectors, but it's enough to think about a simple scalar wave like this to illustrate the origin of the interference pattern. And actually, if you've studied waves at all before, you might know that it can quickly become a bit of a pain to write things in terms of cosines like this. It's much more convenient to write down a complex wave, e to the I times phi. The idea here is that we're using Euler's identity, which says that e to the I times something is equal to the cosine of the thing plus I times the sine of the thing. And so we can think of our original cosine wave as the real part of this complex wave. But exponentials like this are much more convenient to work with than cosines. So this is a useful trick for dealing with classical waves. And it'll be essential when we go to write down quantum mechanical wave function in a minute. Meanwhile, on the opposite side of the barrier, we can write the outgoing waves in a similar way.
I need to understand that. Didn't I open a tab just for his channel? I guess not. This one. All right. Let me see playlist. Okay, not too many videos. So, deriving Earth's orbit, least action explained, Newtonian versus Lagrangian sequence, infinite resistor, physics help room. Gauge field theory. Oh, field theory. Conservation law. And he has good videos. The catenary. Catenary? Catenary? Right, so he doesn't discuss waves. So I need to I need to learn about just the wave equation. Just the wave equation. Let me try. Israel finally declares war on Lebanon. Okay, let me see. So, let me see what's going on with Lebanon. Let's hear this.
Pain is still felt in Lebanon's pants. While the pain is still felt in Lebanon's pants over the attacks, the exploding pagers a couple of days ago and exploding walkie-talkies yesterday, Israel today seemingly stepped it up a little bit, both rhetorically and militarily. In Lebanon, militarily, rhetorically, the IDF spokesperson said we are entering a new stage in the war, referring to it as a war, acknowledging something that has been the case since October 7th or 8th or 9th or whenever Lebanon, through Hezbollah, started firing rockets at Israel daily. Israel also stepped it up militarily. Now Israel has been retaliating in Lebanon on a pretty much daily basis, but today it kind of went in a bit stronger, bombed places with seemingly a little bit less regard for civilians, which of course is great. Again, all this we know from reports in the media, which are limited because Israel limits what they say, rightfully so, because when we're listening, so is the enemy, and of course Hezbollah is a terrorist organization, and they will very much tell you what they want you to know in order to think what they want you to think. But yeah, it looks like a new stage. 2 Israeli soldiers were also killed, so Hezbollah is still very much active, despite the damage that has been done to some of their high-ranking officials through their communication devices. But this is a moment where we've been saying that this is a moment where Israel really needs to act, needs to step it up, and not just needs to step up the bombing campaign, which is very nice to see, but needs to really go in with full force. There are things that Israel has been getting away with in Gaza, and even that's difficult to say because hundreds of soldiers have died in Gaza, including 4 just yesterday. But getting away in a sense with fighting Hamas that they will not get away.
Yeah, my position is that Israel should be very strong. I believe in the rule of law. In general, in a wealthy country, we shouldn't need the rule of law, but Israel is very poor, so it has no choice. The Middle East is very poor, so you have to use force, otherwise it's hopeless. In general, I wish Israel would become wealthier. I wish the Middle East will become wealthier, but that's not going to happen. So you have to use force. I don't know what else. I don't have a third option. It's either become wealthy, so there's no need for violence, or use violence to destroy violence, to have peace. That's it. There's 2 options. There's no third option.
Away with fighting Hezbollah in the north. Hezbollah has a much stronger army, has been able to do a lot more. Israel didn't have any sort of control over any of Lebanon's border except the border with Israel. So anything that comes in from Syria or anywhere else, Israel can't really stop, although sometimes it did. So a war with Lebanon will be much more difficult, and so the things Israel did in Gaza would be insufficient. They're insufficient in Gaza, but in Lebanon they could be disastrous. It could be a bloodbath.
I wouldn't be surprised that the Hezbollah is hiding a lot of munitions under civilian buildings. So they would probably, inside civilian buildings, they would also store weapons so that Israel cannot attack these weapons. Israel will not attack these weapons because Israel is afraid of the world, and the world hates Israel because Israel is Jewish. The world seems to hate Jews. So, Israel needs to bite the bullet, blow up buildings. Any building that is used for any military use needs to be, I don't care about the building, but whatever military use needs to be destroyed, because that military use is used against Israeli civilians. So the Lebanese civilians need to tell the Hamas terrorists, you're not going to store any military equipment in our building because Israel will kill us. And that's it. It's going to happen once, twice, 3 times. It's going to be over, and Hezbollah is going to be neutralized, and it's going to be over. So, a few people will die, yeah. I don't even know if a few people need to die. Israel does the knock, whatever. So they spread notes and they tell people, you have to evacuate. We're blowing up this building in 10 minutes. You have 10 minutes to evacuate the building, even 1 minute. In 60 seconds, you need to evacuate. That's not enough time for the terrorists to evacuate their weapons. So you have 60 seconds. In 60 seconds, you destroy either the building or the equipment, doesn't matter. People had 60 seconds to leave. You survived, good. You didn't survive, too bad. You had 60 seconds. We cannot give you more time because then they take out the equipment. Now, if there's actual terrorists there, then there's no knock. You just blow it up. People need to know, listen, you have a terrorist, a militant in your building, you're going to die. Don't allow these terrorists into your country. Now, Israel actually needs to declare war against Lebanon because Lebanon has Hezbollah, and Hezbollah is attacking Israel as if it's like a separate army, but it's Lebanon. It's coming from Lebanon, and Hezbollah is a Lebanese political party. So Lebanon has declared war against Israel. Why is Israel not reacting?
For Israel, unless Israel really clears whatever, first of all, clears whatever area it wants to enter with ground troops from the air, and also goes further into Lebanon, which we haven't seen yet. Now we see elements of it. For example, when Nasrallah, the leader of Hezbollah, was giving a speech today, or at least a speech of him was broadcast today, Israeli fighter jets were flying in the skies of Beirut and breaking the sound barrier, which I've also heard referred to as some sort of act of aggression. And anything Jews do but die, as we know, is unacceptable to many. But yeah, breaking the sound barrier is nice, but a lot more needs to be broken in Lebanon if Israel is to come out victorious. If Israeli citizens, refugees in their own country, are to be able to come back to their homes in the north of Israel. Welcome to the Daily Objective. This is the third day in a row that we're talking about events in Lebanon, and we're glad that we can finally talk about events in Lebanon.
Mm-hmm. Oh, the covariant.
Good morning, Tensor friends. In my studies of relativity, I keep flinging myself in front of the wheels of progress by asking the fundamental questions. And I've always been that way. I think that's why I was such a bad student. Why? Anyway, that's not the point. So I was using this yesterday, and I said, why does this Christoffel the symbol have this index in the contravariant position? And so I started digging into it, and once again, it turned out to be really simple. And it was fun, so I thought I'd share it with you.
Yeah,
All right,
I need to study this notation. The covariant, the variant, whatever, invariant, contra covariant.
In Springfield, they're eating the dogs, they're eating the cats, eat the cat, eat the cat. They're eating the dogs, they're eating the cats, eat the cat, eat the cat. They're eating the cats, they're eating the dogs, eat the cat, eat the cat, eat the cat, eat the cat. Say ran, so don't push me, ain't Donald Trump trying to grab a bite.
Let's say,
Hello everybody, can you hear me? How you doing? How you feeling? We're having a great 2 days. How y'all doing? I want to see that you can hear me first. Okay. Can you hear me? Can you see me? Are we live? Shayna, welcome to the live stream. Subscribe to Patreon, follow her back on Instagram and Twitter. Hit the thumbs up. It helps to recommend the channel to more people. Thank you. Yes, thank you, Shayna. Hey, nice to see you. I feel like it's been a while since I've seen you. Somebody's worried. I was afraid that you fell. To be honest, valid. Not far from reality. Almost did. How you all? So I'm thinking.
All right, what do we got?
Hi everybody, Physics Ninja here. Today what I want to do is look at transverse waves on a string. What we're going to do is grab the string. It has some tension in it, and it has a certain size. We're going to wiggle our hands up and down in order to create a traveling wave on that string. There are many things that I want to do to describe the wave. First of all, I'm going to show you the expression to describe a wave traveling on a string. We're going to use that expression to learn how to calculate different quantities associated with waves. For example, what is the amplitude of the wave? What is the frequency, the wavelength, the period, the wave number, the angular frequency, and so forth. How do you use this information, for example, to calculate how fast the wave is moving, right? The speed of the wave. And maybe we can use some of these quantities to help us understand what the tension is in the string. I'm also going to show you how to calculate, for example, the velocity of any little segment of rope. Every little segment of rope on a transverse transverse wave simply moves up and down. It has a vertical velocity that depends on its position and on the time. It also has an acceleration. At some point, it's going up, it's going down, it's changing directions. So there is an acceleration associated with this. And given any kind of general expression for a wave traveling on a string, I want you to be able to calculate the direction that this wave is moving. Right? We should be able to just look at the expression and determine whether it's moving to the right or to the left. All right. After the tutorial, what we're going to do is I'm going to give you 2 problems to work on. Right? We'll first read the problem, and then I want you to work it out for yourself. Make sure you understand how to do it. Then you can watch the solution. All right. So 2 problems. Like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support FT. Now that string. All right, so this is what we're going to do. Consider a string here where there is a tension in that string. The tension force is given by Ft. Now that string has a mass and it has a total length L. I'm first going to simply define something called the linear mass density. Okay, so it's mass density. And we call it linear because we're simply dealing basically in one dimension over here. The mass density is simply the total mass of the string divided by its total length. Okay, this is going to be an important quantity that we're going to use in a little bit. Now, when you grab a string like this and have a tension T in it, and you start moving your hand up and down, you're going to create waves. Okay, and those waves are going to propagate along the string, and the waves are in this case going to move to the right like this. Okay, and they're going to move at a speed v. Now, if you apply Newton's second law to any little segment of rope here, what you would find is something called a wave equation. And I'm not going to derive that in this video here. That's not the purpose of it. We simply want to look at solutions to this wave equation. But this is what the wave equation looks like. It says that any element of string at a position y, so y is the vertical displacement, x is...
I saw a video before where he derived it. But really what I want is wave equation derivation. Intro to waves. Simple harmonic motion.
Hi everybody, Physics Ninja, and welcome to my tutorial on simple harmonic motion. In this video, we're going to look at the horizontal spring and mass system. We're going to stretch it, let it go, and we're going to be able to analyze the forces. From the forces, we're going to find equations that describe the position, the velocity, and the acceleration. You're also going to understand how to calculate the period, frequency, and angular frequency of the motion of a simple harmonic oscillator like this. We're going to throw in some example problems to make sure you understand how to use the equations. And the second part, we're also going to look at energy in the system. Right? We're going to look at the potential energy that gets stored in the spring once it gets stretched, and then gets converted into kinetic energy of the mass once it gets moving. All right, let's get started. Like with all my videos, if you like it, give it a thumbs up. Consider subscribing to... And the motion, we may have a lot of questions regarding this motion. The first thing we notice is that the motion the mass oscillates back and forth, and this simply repeats itself over and over again. Right? We may have a lot of questions about this. One might be like, how long does it take for the mass to go back and forth to complete one cycle? This is something we call the period of oscillation, right? We're going to call that T. That's going to be measured in seconds. Well, how do we calculate the period of oscillation? What factors into the period of oscillations? How do I make the period bigger or smaller, right? Those are questions you might have. What do I have to change? I may be interested in calculating the position of this mass as a function of time. I may also be interested in what is the maximum kind of displacement of this mass. In addition, we're always interested in other kinematic quantities like the velocity and the acceleration. Once you get to acceleration, you're thinking, well, what causes all of this motion, right? Then we get into the questions of forces, right? What kind of forces are acting on this mass in order to produce this periodic motion? Later on in the video, we're going to talk about energy. Like, is energy conserved in the system? And if so, what type of energy is there? You see that the mass is moving, so there's energy associated with the motion, right? So this is what we call kinetic energy.
I want to show you the equation of a wave and explain to you how to use it. But before I do that, I should explain, what do we even mean to have a wave equation? What does it mean that a wave can have an equation? Here's what it means. So imagine you've got a water wave and it looks like this. We graph the vertical height of the water wave as a function of the position. So for instance, say you go walk out on the pier and you go look at a water wave heading towards the shore. So the wave might move like this. You'll see this wave moving towards the shore. Now, realistic water waves on an ocean don't really look like this, but this is the mathematically simplest wave you could describe. So we're going to start with this simple one as a starting point. So let's say this is your wave. You go walk out on the pier and you go stand at this point, and the point right in front of you, you see that the water height is high. And then 1 meter to the right of you, the water level is 0. And then 2 meters to the right of you, the water height, the water level is -3. What does that mean? It means that if it was a nice day out, right, there's no waves whatsoever, there'd just be a flat ocean or lake or wherever you're standing. But if there's waves, that water level can be higher than that position or lower than that water level position. We'll just call this water level position 0, where the water would normally be if there were no waves. So you graph this thing and you get this graph like this, which is really just a snapshot. Because this is vertical height versus horizontal position, it's really just a picture. So in other words, I could just fill this in with water and I'd be like, oh yeah, that's what the wave looks like at that moment in time. And if I were to show what the wave does, it travels toward the shore like this and you'd see it move. So that's what this graph really is. If you've got a height versus position, you've really got a picture or a snapshot of what the wave looks like at all horizontal positions at one particular moment in time. And so what should our equation be? It should be an equation for the vertical height of the wave that's at least a function of the position. So this is function of, this isn't multiplied by, but this y should at least be a function of the position, so that I get a function where I can plug in any position I want. Let's say x equals 0, and it should tell me, oh yeah, that's at 3. So this wave equation should spit out 3 when I plug in x equals 0. When I plug in x equals 1, it should spit out, oh, that's at 0 height. So it should give me a y value of 0. And if I were to plug in an x value of 6 meters, it should tell me, oh, yep, that y value is -3. So no matter what x I plug in here, say 7, it should tell me what the value of the height of the wave is at that horizontal position. So what would this equation look like? Well, let's just try to figure out y should equal as a function of x. It should be no greater than 3 or -3, and this is called the amplitude. So if we call this here the amplitude A, it's going to be no bigger than that amplitude. So in this case, the amplitude would be 3, but I'm just going to write amplitude. So this is a general equation that you could apply to any wave. And then look at the shape of this. This is like a sine or a cosine graph. Which one is this? Well, because at x equals 0, it starts at a maximum. I'm going to say this is most like a cosine graph because cosine of 0 starts at a maximum value. So I'm going to say that this is like cosine of some stuff in here. Now you might be tempted to just write x, but that's not going to work. If I just wrote x in here, this wouldn't be general enough to describe any wave. Because think about it. If I've just got x, cosine of x will reset every time x gets to 2 pi. So every time the total inside here gets to 2 pi, cosine resets. Look at this cosine. It resets after 4 meters. And some other wave might reset after 8 meters. And some other wave might reset after a different distance. I need a way to specify in here how far you have to travel in the x direction for the wave to reset. So x alone isn't going to do it, because if you just got x, it always resets after 2 pi. So what do? I play this
the same game that we played for simple harmonic oscillators, and I say that this is 2 pi, and I divide by not the period this time. This is not a function of time, at least not yet. It's not a function of time. This is just of x. So this wouldn't be the period. This would not be the time it takes for this function to reset. It would actually be the distance that it takes for this function to reset. In other words, what we call the wavelength. So the distance between two peaks, called the wavelength, and we represent it with this Greek letter lambda. So the distance it takes a wave to reset in space is the wavelength. That's what we would divide by, because that has units of meters. And then finally, we would multiply by x in here. That way, if I started x equals 0, cosine starts at a maximum, I would get 3. If I say that my x has gone all the way to one wavelength, and in this case it's 4 meters, like all the way 4 meters or one wavelength, once I plug in wavelength for x, that wavelength would cancel this wavelength, we get 2 pi, and this cosine would reset, because once the total inside becomes 2 pi, the cosine will reset. And that's what happens for this wave. It should reset after every wavelength. You go another wavelength, it resets. Another wavelength, it resets. And that's what would happen here. So how would we apply this wave equation to this particular wave? Well, let's take this. It's already got cosine, so that's cool because I've got this here. You could use sine if your wave started at this point and went up from there, but ours starts at a maximum, so we'll use cosine. So we'll say that our amplitude, not just A, our amplitude happens to be 3 meters because our water gets as high as 3 meters above the equilibrium level, and we'll leave cosine in here. The 2 pi stays, but the lambda does not. Our wavelength is not just lambda, that's just too general. We gotta write what it is, and it's the distance from peak to peak, which is 4 meters, or you can measure it from trough to trough, or you can call these valleys valley to valley. That'd also be 4 meters. Regardless of how you measure it, the wavelength is 4 meters. And then what do I plug in for x? I don't, because I want a function. This is a function of x. I mean, I can plug in values of x. Let's do it. Let's see if this function works. If I leave it as just x, it's a function. It tells me the height of the wave at any point in x, but we should be able to test it. Let's test if it actually works. So let's take x and let's just plug in 0. So if I plug in 0 for x, what does this function tell me? It tells me that the cosine of all of this would be 0. And I know cosine of 0 is just 1. So tell me that this whole function is going to equal 3 meters. And that's true. The height of this wave at x equals 0. So at x equals 0, the height of the wave is 3 meters. So that one worked. Let's try another one. Let's say we plug in a horizontal position of 2 meters. If I plug in 2 meters over here, and then I plug in 2 meters over here, what do I get? This is going to be 3 meters times cosine of, well, 2 times 2 is 4, over 4 is 1, times pi, so we cosine of just pi. And the cosine of pi is -1. So I'm going to get -3 out of this. -3 meters, and that's true. The height of this wave at 2 meters is -3 meters. So this function is telling us the height of the wave at any horizontal position x, which is pretty cool. However, you might have spotted a problem. You might be like, wait a minute, that's fine and all, but this is for one moment in time. This wave's moving. Remember, this whole wave moves toward the shore. So at a particular moment in time, yeah, this equation might give you what the wave shape is for all values of x. But if I wage at the moment, oop, now everything's messed up. Now at x equals 2, the height is not -3. And at x equals 0, the height is no longer 3 meters. It only goes up to here now. So what do we do? How do we describe a wave that's actually moving to the right in a single equation? Well, it's not as bad as you might think. Let me get rid of this. Let's clean this up. We're really just going to build off of this function over here. What I really need is a wave equation that's not only a function of x, but that's also a function of time. So this function up here has to not just be a function of x, it's got to also be a function of time. So I can plug in any time and any position, and it would tell me what the value of the height of the wave is. So how do I get the time dependence in here? Well, I'm going to ask you to remember, if you add a phase constant in here, remember if you add a number inside the argument to cosine, it shifts the wave. In fact, if you add a little bit of a constant, it's going to take your wave, it actually shifts it to the left. So we're not going to want to add. If we've got a wave going to the right, we're going to want to subtract a certain amount of shift in here. But subtracting a certain amount, so that's cool, because subtracting a certain amount shifts the wave to the right. But if I just had a constant shift in here, I wouldn't do it. Like the wave of the beach does not just
I always
single
get
equation
confused with this
telling us the height of the wave
shit.
at any horizontal position x, which is pretty cool. However, you might have spotted a problem. You might be like, wait a minute, that's fine and all, but this is for one moment in time. This wave's moving. Remember, this whole wave moves toward the shore. So at a particular moment in time, yeah, this equation might give you what the wave shape is for all values of x. But if I wage at the moment, oop, now everything's messed up. Now at x equals 2, the height is not -3. And at x equals 0, the height is no longer 3 meters. It only goes up to here now. So what do we do? How do we describe a wave that's actually moving to the right in a single equation? Well, it's not as bad as you might think. Let me get rid of this. Let's clean this up. We're really just going to build off of this function over here. What I really need is a wave equation that's not only a function of x, but that's also a function of time. So this function up here has to not just be a function of x, it's got to also be a function of time. So I can plug in any time and any position, and it would tell me what the value of the height of the wave is. So how do I get the time dependence in here? Well, I'm going to ask you to remember, if you add a phase constant in here, remember if you add a number inside the argument to cosine, it shifts the wave. In fact, if you add a little bit of a constant, it's going to take your wave, it actually shifts it to the left. So we're not going to want to add. If we've got a wave going to the right, we're going to want to subtract a certain amount of shift in here. But subtracting a certain amount, so that's cool, because subtracting a certain amount shifts the wave to the right. But if I just had a constant shift in here, I wouldn't do it. Like the wave of the beach does not just move to the right and then boom, it just stops. It just keeps moving. We need a wave that keeps on shifting. So you might realize, if you're clever, you'd be like, wait, why don't I just make this phase shift depend on time? That way, as time keeps increasing, the wave's going to keep on shifting more and more. So if this wave shift term kept getting bigger as time
This is not the best way to draw it, because you need to imagine an animation. That's difficult. So the way I would do it is in 3D. So I would have xy, xt. Anyway, I would have another dimension, which is t. And then t, let's say t goes into the board, into the screen. And then you would have, and then x would be a function of t. But you don't want x to be a function of t, do you? You want x and t to be independent. I don't know.
got bigger, your wave would...
Because you have two independent variables, x and t.
keep shifting to the right. You'd have an equation that describes a wave that's actually moving. So what would you put in here? It might seem daunting. You might be like, man, that's gonna be complicated. How do we figure that out? But it's not too bad, because just like the wavelength is the distance it takes for the wave to reset, there's also something called the period. We represent that with capital T, and the period is the time it takes for the wave to reset. So if I wait one whole period, this wave will have moved in such a way that it gets right back to where you couldn't really tell. It looks like the exact same wave, in other words. So we show that over here. Let's say you had your water wave up here. I take this wave. You wait one whole period, the wave will have shifted right back, and it'll look like it did just before. So that whole wave moving toward the beach. So if you close your eyes and then open them 1 period later, the wave looks exactly the same. So we're going to use that fact up here. We need this function to reset, not just after a wavelength. We need it to reset after a period as well. So how do we represent that? We play the exact same game. We say that, all right, I can't just put time in here. What I'm going to do is I'm going to put 2 pi over the period, capital T, and then I multiply by the time. That way, just like every time x went through a wavelength, every time we walk one wavelength along the pier, we see the same height because this becomes 2 pi. Every time we wait one whole period, this becomes 2 pi, and this whole thing is going to reset again. So this is the wave equation, and I guess we can make it a little more general. This cosine could have been sine. So if you end up with a wave that's better described with a sine, maybe it starts here and goes up. You might want to use sine. And the negative, remember the negative caused this wave to shift to the right. You could use negative or positive because it could shift right with the negative, or if you use the positive, adding a phase shift term shifts it left. So a positive term up here would describe a wave moving to the left. And technically speaking, you can make it just slightly more general by having one more constant phase shift term over here to the right. If we add this, then we could take into account cases that are weird where maybe the graph starts like here and neither starts as a sine or a cosine. You have to draw it shifted by just a little bit. But in our case right here, don't worry about it because it started at a maximum, so you wouldn't have to have that phase shift. And this is it. This is the wave equation. This is what we wanted. A function of position and time. It tells you the height of the wave at any position x, horizontal position x, and any time t. So let's try to apply this formula to this particular wave we've got right here. So let me get rid of this, right? This was just the expression for the wave at one moment in time. So maybe this picture that we took of the wave at the pier was at the moment, let's call it t equals 0 seconds. So t equals 0 seconds, because this picture, that's what the wave looks like. And this is the function that describes what the wave looks like at that moment in time. We're going to do better now. Now we're going to describe what the wave looks like for any position x and any time t. So let's do this. What would the amplitude be? That's easy. It's still 3. The wave never gets any higher than 3, never gets any lower than -3, so our amplitude is still 3 meters. And since at x equals 0 and t equals 0, our graph starts at a maximum, we're still going to want to use cosine. So we come here, 2 pi x over lambda. Well, the lambda is still lambda. So lambda here is still 4 meters because it took 4 meters for this graph to reset. You had to walk 4 meters along the pier to see this graph reset. That's a little misleading. I mean, you have to run really fast. The wave's going to be moving as you're walking. So I should say, if you're standing at 0 and a friend of yours is standing at 4, you would both see the same height because the wave resets after 4 meters. Would we want positive or negative? Since this wave's moving to the right, we would want the negative. I wouldn't need a phase shift term because this starts with a perfect cosine. It doesn't start as some weird in-between function. The only question is, what do I plug in for the period? So I would need one more piece of information. If I'm told the period, that'd be fine. Sometimes questions are trickier than that. Maybe they tell you this wave is traveling to the right at 0.5 meters per second. Let's say that's the wave speed. And you're asked, create an equation that describes the wave as a function of space and time. So you do all this, but then you'd be like, how do I find the period? We have to use the fact that, remember, the speed of a wave is either written as wavelength times frequency, or you can write it as wavelength over period. So I can solve for the period. I can say that the period of this wave, if I'm given the speed and the wavelength, I can find the wavelength on this graph. I'd say that the period of the wave would be the wavelength divided by the speed. So our wavelength was 4 meters, and our speed, let's say we were just told it was 0.5 meters per second, which gives a period of 8 seconds. So we have to plug in 8 seconds over here for the period. And there it is. That's my equation for this wave. This describes, this little equation is amazing. It describes the height of this wave at any position x and any time t. So in other words, I can plug in 3 meters for x and 5.2 seconds for the time, and it would tell me what's the height of this wave at 3 meters at the time 5.2 seconds, which is pretty amazing. So recapping, this is the wave equation that describes the height of the wave for any position x and time t. You would use the negative sign if the wave is moving to the right, and the positive sign if the wave was moving to the left.
That was very nice, but we want the version with the eye.
Hey, what's up? You got Puff here, back at you with another video. This time my hair and my beard are even longer than my previous video because somebody said that my hair and beard were getting too long. No such thing. In today's video, I want to talk to you about something known as the wave equation. It looks something like this, but don't worry, you don't need to have a mathematical background to understand what I'm going to be talking about. As long as you studied physics to high school level or even maths to high school level, then you should follow exactly what I'm saying. And by the end of this video, hopefully you'll have some understanding of what this equation is trying to tell us and why it's called the wave equation. Before we go any further though, I'd quickly like to say, if you enjoyed this video, please do leave a thumbs up, and all that aside, let's get into it. Let's start by labeling a few variables that we see in the wave equation here, specifically the variables x and t. Let's get the easy ones out of the way first. X refers to a spatial direction. Let's say for our purposes that the x direction is toward the right. What this means is that along this line we have different values of x. X is equal to 0, x is equal to 1, x is equal to 2, and so on and so forth. The units don't really matter, we just need to know that this is a spatial direction. And t, as we expect, stands for time. This is because we'll be studying the behavior of waves as time progresses. So we can choose a particular instance when we're studying a wave. We can choose t is equal to 0 to be now, for example, and then we can work out what happens to a wave that we're studying, maybe, I don't know, 5 units of time later, maybe 5 seconds later. And so basically just labeling these two quantities, we'll be able to understand one simple thing about the wave equation. It might seem like a relatively obvious point, but the wave equation studies the behavior of waves in space and in time. In this case, we've got what's known as the one-dimensional wave equation because we've only got x, which is the x direction, one dimension. Now,
Yeah, but why is he starting from an equation? That doesn't make any sense. I'm looking for the I'm looking for the complex version.
It's not a silver bullet. It's how they all work together. And you're talking about U.S. systems, NATO systems, different European systems, and old Soviet systems all working
Wow,
together. That is
only
valid, and
left
that is why,
here.
you know, the Ukrainians continue to be, they're employing all these different types of capabilities on the battlefield and still being very successful at doing that. But it is not one system or capability that's going to be that silver bullet. Yeah.
Thank you, ma'am. I wanted to ask about AUKUS Pillar 2 and kind of
battlefield and still being very successful at doing that. But it is not one system.
Oh,
or
no comment
capability that's
section?
going to be that silver bullet. Yeah.
Thank you, ma'am. I wanted to ask about
Mm-hmm. Mm-hmm. We need to. Oh, she died.
Hello, this is Dr. Grande. Today's question is, can I analyze the case of Jenny Blaylock? Just a reminder, I'm not diagnosing anybody in this video, only speculating about what could be happening in a situation like this. If you enjoyed this, move to the timeline of the incident and offer my analysis.
Why is my internet so slow?
In 2001, she earned a bachelor's degree in human resources from the University of Tennessee. She eventually obtained a general contractor's license and started two businesses, Lux Homes and Design. This was a custom home building and remodeling company, and Plantation Reclaimed Incorporated. This company reclaimed wood from barns. Jenny operated a YouTube channel called TN Fly Girl. In August of 2021, she started uploading videos featuring her efforts to earn a private pilot's license. In June of 2022, she purchased a 1965 Beech 35 C-33 Debonair. This is a single-engine propeller aircraft with retractable landing gear. It is a relatively sophisticated and powerful aircraft for someone learning how to fly. After the purchase of this airplane, many of the videos that Jenny uploaded featured her flying it. By early December 2023, she had 16,000 subscribers and about 750,000 lifetime views. Many of the recent videos have been taken down since the incident that I will talk about in a moment. The channel featured videos of Jenny's experiences through her pilot training, including some of her more challenging times. Here are a few of her video titles that sum up her channel pretty well. What did I miss on my checklist before takeoff? The mystery of my autopilot. Is it possible to fix it? Will we make it before nightfall? Aircraft malfunction at 4,000 feet, emergency landing, and what to do when nothing seems to work. Some of Jenny's videos featured her flying with her father, James. She described him as someone who had, quote, years of flying experience, unquote. Now moving to the timeline of the incident. On December 7, 2023, 44-year-old Jenny Blaylock was with her 78-year-old father, James Blaylock, in her Beech Debonair. Jenny was planning on flying from Knoxville Downtown Island Airport in Knoxville, Tennessee, to Saline County Regional Airport in Benton, Arkansas. These two locations are about 500 miles apart. The purpose of the trip was to get instrument upgrades for the Beech Debonair. Jenny took off at 9:48 a.m. Her father was in the passenger seat. The Debonair climbed to 2,500 feet and stayed there for about 12 minutes before climbing to 6,400 feet. Jenny was flying in clear skies with visibility of 10 miles. It was 53 degrees outside. When the aircraft was about 161 miles into the trip, air traffic control told Jenny that she was left of course. She responded by saying that she was correcting the course. Starting at 10:19 a.m., it appears as though Jenny was experiencing some difficulty maintaining a steady altitude.
10:19 p.m., so that's already dark.
She started a series of descents and climbs. Her altitude varied between 6,400 feet and 5,300 feet. At 10:57 a.m., the Debonair descended down to 4,300 feet, where it was traveling at 164 miles per hour. The aircraft then climbed to 6,050 feet, where it was traveling at 97 miles per hour. At this point, the Debonair entered into a rapid descent. The maximum rate of descent reached 11,900 feet per minute, and the maximum speed reached 262 miles per hour. Descent. The maximum rate of descent reached 11,900 feet per minute, and the maximum speed reached 262 miles per hour.
Wait, what? How fast?
The aircraft then climbed to 6,050 feet, where it was traveling at 97 miles per hour. At this point, the Debonair entered into a rapid descent. The maximum rate of descent reached 11,900 feet per minute.
What kind of speed is that? 11,000 feet? I don't know what kind of speed is that. 11,000 feet per minute. Who talks this way? Like, how many miles per hour, knots per hour? Like, what's going on?
And the maximum speed reached 262 miles per hour.
Okay.
Air traffic control attempted to make contact with Jenny, but she did not acknowledge them. Then they received a communication from Jenny, where she stated the airplane's registration, the word Debonair, an emergency declaration, and finally, an unintelligible word. About a minute later, a communication was also received from the passenger, James, but it was largely unintelligible. At 11:03 a.m., Jenny's aircraft slammed into a wooded area near Pulaski, Tennessee. Here's what investigators found at the crash site. The bodies of Jenny and her father were recovered near the wreckage. Presumably, they died due to the collision with the ground. A witness told the media that one of the victims was on fire when emergency services arrived. The debris field was about 300 feet long, and several treetops leading to the wreckage were chopped off at progressively lower heights. This appeared to reveal the path of the aircraft. Impact forces and fire destroyed the cockpit, and the flight control system components were all destroyed or significant. This appeared to reveal the path of the aircraft. Impact forces and fire destroyed the cockpit, and the flight control system components.
The problem is the fire. I don't know if they would have died just from the crash.
Were all destroyed or significantly damaged. No flight instrumentation or gauges were recovered. The settings for the autopilot could not be determined. The elevator trim tab was set at about 5 degrees of deflection in the nose down.
Is there a black box?
On direction. The maximum deflection in this direction for this aircraft was 10 degrees. Investigators found 2 digital recording devices of deflection in the nose down direction. Impact forces and fire destroyed the cockpit and the flight.
This is impossible. I can't go back and forth. I mean, I'm dying here. Why is it so impossible to go back and forth? Jesus Christ, it's impossible. I don't know what to do. Well, I mean, I don't have, it's because I have something on that's like killing it? What? Let me close some windows. Nothing heavy. I'm not doing anything. I'm basically one window. Let me close this window and this window and this window. Let's try again.
Control system possibly lower heights. This appeared to reveal the path of the aircraft. Impact forces and fire destroyed the cockpit, and the flight control system components were all destroyed or significantly damaged. No flight instrumentation or gauges were recovered. The settings for the autopilot could not be determined. Some components were all destroyed or significantly damaged. No flight instrumentation or gauges were recovered. The settings for the autopilot could not be determined. The elevator trim tab was set at about 5 degrees.
The elevator trim pad set for 5 degrees. Elevator trim? That's like, what's that?
Of deflection in the nose down direction. The maximum deflection in this direction for this aircraft was 10 degrees. Investigators found 2 digital recording devices.
So she was half pointing down? Why?
Which were intact and will no doubt be examined further. These were almost certainly the cameras that Jenny was using to produce videos for social media. A witness stated that right before the crash, the aircraft was flying at high speed and the engine was running.
Oh my God, this is impossible. Why is it buffering? There's plenty of buffering. The buffering is not the reason. Why is it blocking? It's basically a brand new computer. There shouldn't be an issue with it.
The aircraft was not in a stall and it was not spinning. The preliminary report from the National Transportation Safety Board did not identify any obvious cause for the crash. Now moving to my analysis. Here are my thoughts in a few areas that stood out to me in this case. Item number 1. Jenny had about 400 hours of total flying time when she was killed in the crash, although her skill level was consistent with someone with fewer hours. From the videos that she released, it's clear that Jenny didn't really understand the physics of flight or how the aircraft instruments functioned.
Wonderful.
It's almost like she didn't make the connection about how her inputs via the flight controls affected the control surfaces
So how did she get a license?
of the aircraft. She wasn't comfortable with the basics and became overwhelmed when she had to attend to other responsibilities of flying, like watching the instruments, looking outside the aircraft, and communicating with air traffic control. Following a set of procedures was not the strength of Jenny's, although this is a critical element for safely flying. For example, in a few flights, she didn't properly go through the necessary checklists or pay attention to them in a way consistent with survival. During one takeoff, Jenny said gear down as she was putting the gear up. She may not have fully understood what the terms gear up and gear down actually meant. Item number 2, during one video, Jenny landed at an airport and drove to a local restaurant in a motor vehicle. During the drive, she failed to stop at stop signs and almost hit another vehicle when merging onto a road. In the comments, Jenny referred to her stop sign behavior as rolling stops. Her dangerous and cavalier driving style is consistent with a person who simply has no respect for the safety of the public or who is oblivious to the world around them. Ironically, Jenny drove with her head in the clouds. Item number 3, Jenny seemed to be impatient and a little bit
I
sensational.
don't know. Why is it buffering all the time? Jesus, let me refresh
So this
this.
is Dr. Grande. Today's question is, can I
Are you
analyze the case
kidding
where Jenny's
me?
attitude is unrealistic? A challenging discussion that the CFI needed. Eventually, she realized that pressing forward with a dangerous and cavalier driving style is consistent with a person who simply has no respect for the safety of the public or who is oblivious to the world around them. Ironically, Jenny drove with her head in the clouds. Item number 3, Jenny seemed to be impatient and a little bit sensation-seeking. In her videos, some of her frustration centered around how she wasn't learning fast enough. Eventually, she realized that pressing forward without the necessary skills would be reckless. Jenny moved from one certified flight instructor, or CFI, to another, and kind of went back to basics. Not surprisingly, she struggled tremendously to control the aircraft. Jenny did not understand the basics of flight. Whenever someone is teaching another person how to do something, regardless of the industry, there is an assumption that the trainee is going to learn what they need to learn. Success is the expected outcome. Unfortunately, that attitude is unrealistic. The challenging discussion that the CFI needed to have with Jenny was how flying a plane is not for everyone. Some people should not pursue a private pilot's license. Perhaps Jenny could have satisfied her desire to fly by using a flight simulator, where high-velocity ground encounters are associated with emotional consequences only. Item number 4, consistent with her impatience and her desire to press forward rapidly, Jenny purchased a Beech Debonair. Right away, she experienced difficulties with this high-performance aircraft, describing it as a rocket compared to what she was used to flying. She suggested that the plane's tendency to climb was alarming, and she had difficulty controlling it. Typically, a pilot in training would not opt for an aircraft as powerful as the Debonair. This was way too much plane for her skill level. Jenny struggled with many of the features of the aircraft, but she had a substantial amount of difficulty with the autopilot. This particular aircraft was equipped with a Century 2000 autopilot. Before describing her challenges with autopilot, I first need to describe the concept of trim in an aircraft. The aircraft moves around 3 axes. The lateral axis, this is the pitch or up and down movement of the nose.
So this guy knows how to fly. Maybe he has a license. All right, so we have pitch, lateral axis. This is the lateral axis. Longitudinal axis, this is roll. And vertical axis, this is yaw. Okay. Okay, so pitch basically means point the nose up and down. Roll means point, let's say, the right wing up and down. And yaw means point the tail right and left.
The vertical axis, this is the yaw, or the right and left movement of the nose. And the longitudinal axis, this is the roll, or the plane banking, right or left. Trim can
Banking, right.
relate to all three of these depending on the aircraft, but in this description, I'm talking about the up and down movement of the nose. The vertical axis, this is the yaw, or the right and left movement of the nose. And the longitudinal axis, this is the roll, or the plane banking, right or left. Trim can relate to all three of these depending on the aircraft, but in this description, I'm talking about the lateral axis, the pitch of the aircraft.
So she had a trim of 5 degrees. That's crazy. That means the plane wanted to roll to. Let me see what he says.
Or left. Trim can relate to all three of these depending on the aircraft, but in this description, I'm talking about the lateral axis, the pitch of the aircraft.
So she set the pitch, meaning the nose. She set the nose down like 5%. He says that's half of maximum.
Which is controlled by the elevators. Pilots use the control column or yoke to control the elevators.
So the elevators are these guys in the back. So pitch is controlled by these guys. She set the trim to 5% down, meaning nose down or nose up.
The lateral axis, the pitch of the aircraft, which is controlled by the elevators. Pilots use the control column or yoke to control the elevators and maintain a desired pitch attitude. This could be nose up, nose down, or level flight. The problem with this is that the pressure exerted.
What did he say? Yoke?
The lateral axis, the pitch of the aircraft, which is controlled by the elevators. Pilots use the control column or yoke to control the elevators and maintain.
Yoke, not the yaw. The yoke is the actual wheel or the stick.
Lateral axis, the pitch of the aircraft, which is controlled by the elevators. Pilots use the control column or yoke to control the elevators.
The control column, that's the stick.
And maintain a desired pitch attitude. This could be nose up, nose down, or level flight. The problem with this is that the pressure exerted on the elevators by the air is transmitted through the yoke. This means that the pilot must exert energy to keep the elevators in a certain position. Using the trim controls in the aircraft, which control trim tabs on the elevators, the pilot can reduce or eliminate the excess pressure and return the yoke to a neutral position, meaning the pilot doesn't have to exert any energy to keep the yoke in one place. This trim control feature is much more than a convenience. It is really necessary. A pilot who becomes tired of holding the yoke in one position is not going to attend well to other responsibilities. Trim makes flying safer and more comfortable. Some aircraft are equipped with automatic trim, but the Debonair that Jenny had did not have this feature. She needed to manually adjust the trim using the trim wheel control in the cockpit. Moving back to the autopilot, the Century 2000 controls the elevators in order to maintain a desired pitch attitude. It does not manage the trim, and it does not manage the power. The servos in the system can get overworked if the aircraft is out of trim. Therefore, trim indicators on the autopilot flash and direct the pilot to adjust the trim as needed. This is really not a big deal for most pilots. They see the indicators flashing, they adjust the trim in the direction indicated, either up or down, and they continue flying. In one video where Jenny was trying to use the autopilot, she ignored those trim indicators. Furthermore, the buttons on the autopilot are momentary push style.
Why did she get a license?
And she was holding.
Why was she given a license?
Them down. There's a sense that Jenny did not understand the concept of trim. Direction indicated, either up or down, and they continue flying. In one video where Jenny was trying to use the autopilot, she ignored those trim indicators. Furthermore, the buttons on the autopilot are momentary push style, and she was holding them down. There's a sense that Jenny did not understand the concept of trim and how it related to the autopilot. She didn't know what direction to spin the trim wheel based on the indicators, even though the indicators were literally labeled trim up and trim down, the same label seen on the trim control wheel. Jenny found herself in the habit of turning the autopilot off, trimming the airplane, and reactivating the autopilot, instead of simply trimming the pressures off the elevators as directed by the autopilot. If Jenny didn't understand the autopilot, it stands to reason that she did not understand other aircraft components or systems either. Item number 5. Jenny had installed cameras in her airplane in order to capture her experiences for social media. Not only did she have a YouTube channel, she had an Instagram page. Clearly, her social media presence was important to her. Some people have suggested that these cameras could have functioned as a distraction. I think this is certainly possible, but there's something else about her recording that is more worrisome. There is the sense that Jenny was looking for dramatic situations to record. Several of her videos emphasized dangerous situations. She believed that a video featuring an in-flight emergency was going to be more effective at attracting viewers than a video with a title like, "I flew my airplane and absolutely nothing went wrong." Jenny may have been correct in her assumption, but I think this created a temptation to experiment while flying the aircraft. The autopilot is a great example. Instead of reading the manual for the autopilot on the ground and learning how it functioned, she kept trying to figure it out while flying. The cameras may have been a distraction, but I think the performance that Jenny put on for the cameras was the real problem. That was the form of the distraction. Now moving to my final item, number 6. What do I think happened in this case? This is just a theory, my opinion. Jenny was not well suited to fly an airplane and did not have a set of motives consistent with her continued survival. She was simply not learning what she needed to learn. With her low level of skill, just about anything could have gone wrong. Many obvious causes for the crash have been eliminated. Jenny did not stall, the plane was not in a spin, and no component of the aircraft was missing. This was not a case where a propeller or part of a wing fell off in midair. I think it is reasonable to believe that this aircraft crashed because Jenny supplied inputs through the flight controls that directed the aircraft into the ground. This wasn't a mechanical failure, it was a pilot error. The question, of course, is this: what kind of error was it? Why did she supply fatal inputs? Some have speculated that the autopilot trim situation could have led to the crash. This is a good theory. However, Jenny knew how to disconnect the autopilot. She had done this before in another video where she was struggling. It doesn't make sense that she simply didn't pull back on the yoke when the plane was descending. Maybe her arms were tired from fighting the autopilot.
But she didn't know she was descending. If she doesn't know how to read instruments, she was flying now at night in the dark over a wooded area, so maybe there's no light. So she had no idea where she is, going up, down, right, left. She had no idea.
Autopilot.
And she probably did not know how to read the instruments.
40 minutes, or she didn't have the physical strength. Another possibility is that Jenny went into a panic after struggling for 40 minutes unsuccessfully to maintain a steady altitude. Spatial disorientation is also a possibility in these types of cases.
Plus, it's a very long flight, 500 miles. At about 100 miles an hour, that's 5 hours, 4 hours, 3 hours, 2 hours, even 1 hour. That's endless. You have to have an autopilot. So she was sitting there struggling for an hour. Jesus.
Cases as well. Jenny didn't understand the position of the aircraft relative to the ground. At the time making this video, there is no way to know the cause of the crash. Overconfidence, less than ideal training, impulsivity, impatience, panic, and a lack of skill are all possibilities as factors that could have contributed to the crash. Jenny had a lot of tools at her disposal to bring a plane down. If she had only been as well equipped to fly a plane, this disaster could have been avoided. Now moving to my final thoughts. I think the theme of this case is how Jenny didn't give up. In a broad sense, she didn't discontinue her flight training, even though that would have been a wise choice. In a specific sense, she fought with her aircraft for 40 minutes instead of trying something different, like turning the autopilot off or simply landing. If the autopilot did cause the crash, the irony is that Jenny was figuratively on autopilot during her training, therefore never literally learned how to use the autopilot. Those are my thoughts in the case of Jenny Blaylock. Please put any opinions and thoughts in the comment section. They always generate an interesting dialogue. As always, I hope you found my analysis of this topic to be informative. Thanks for watching.
Wow, that was incredible.
Hello, this is Dr. Grande. Today's question is, can I analyze the case of Macy Marie Lathers? Just a reminder, I'm not diagnosing anybody in this video, only speculating about what could be happening in a situation like this. If you enjoyed this video, please like it, subscribe to my channel, and consider supporting me on Patreon. I will put a link to Patreon in the description for this video. First, I'll look at the background of this case, move to the timeline of the crime, then offer my analysis. Macy Marie Lathers was born in June 2000 and lived in Fort Plain, New York. This small
It's difficult to know if she's pretty, because any girl can look like this.
town is about an hour west of Albany.
Even a guy can look like this. So it's the any you need to have many more pictures to begin to understand if a person is beautiful or not.
She graduated from college and in 2022 moved to Florida. Macy represented herself as an entrepreneur and a model, claiming that she was affiliated with 2 modeling agencies. She started an Instagram account which has over 14,000 followers, although some of those followers were added after the incident I will be talking about in a moment. I believe she had about 11,000 prior to the incident. In her bio, Macy indicated that she had money on her brain and was lit in real life. The images and videos featured on her Instagram account appear to indicate a party lifestyle, complete with luxury vehicles, yachts, and expensive hotels. Macy had a particular fascination with her own posterior region, as it was often the target of her camera. On January 16, 2024, Macy's driver's license was suspended. However, she continued to drive her Mercedes-Benz sedan. Now moving to the timeline of the crime. On August 10, 2024, just after 6:45 a.m., Macy was traveling south on North Miami Avenue in her Mercedes-Benz. As she approached a red light at the intersection with North 8th Street, Macy failed to stop. Her vehicle ran through the red light and slammed into a black Range Rover. After this initial collision, both the Mercedes and the Range Rover slammed into a silver Suzuki. The driver of the Range Rover suffered minor injuries. There were 3 people in the Suzuki. 1 was killed instantly. 1 was taken to a hospital and died.
That's a tiny car. So, and it's hit from the side. Yeah, like most cars are basically unprotected for that. Plus, it's an old car. It's a tiny car. Yeah.
And 1 survived with injuries. It appeared as though Macy suffered no injuries or minor injuries in the collision.
Right. So, it's a new car, and it's a frontal hit, and the engine protected her.
She could be seen on video surveillance walking on the sidewalk headed north on North Miami Avenue.
Okay.
The hood of her sweatshirt was pulled up as if she was trying to hide her face from cameras. After walking several hundred feet, Macy crouched down on the sidewalk for a few seconds, then stood up and continued walking in the same direction before abruptly turning around. Now she was walking back toward the fatal collision that she had caused. She mixed in with several other people who were jogging in the area and walked to the scene of the collision. The authorities would later indicate that bystanders confronted Macy and made her return to the scene, but no confrontation was captured on the released video. At the scene, the body cameras of first responders captured Macy on the ground.
Why is she shirtless?
Screaming and vomiting. She told the police that she was on a party drug referred to as 2C, which is technically called 2CB. The investigation into the collision revealed that 5 seconds before it happened, Macy was traveling at 57 miles per hour. The accelerator was at 100%, so her foot was to the floor. At the time of the collision, she was traveling 78 miles per hour. Macy was arrested and charged with several offenses, including 2 counts of vehicular.
Yeah. So she has bad skin. Her eyes are droopy. Yeah. But she could be beautiful. I don't know. But she doesn't have a good body. You could see when she was walking, she doesn't have a good body.
Homicide, reckless driving, driving with a suspended license, and causing injury. Initially, she was held on house arrest, but this changed after her toxicology report came back. She had a variety of drugs in her system, although not alcohol. Macy was charged with 2 counts of DUI manslaughter and held without bond. The judge said, "I think she's extremely dangerous." Now moving to my analysis. The drug 2CB is both a stimulant and a hallucinogen. It is also referred to as Nexus and pink cocaine. The drug is part of the 2C family of synthetic psychedelic drugs.
So because drugs are basically illegal, it's called a controlled substance, which means it's illegal. So there is no control over this substance. So people take it without a prescription, without any medical oversight. So I think like people should be able to do drugs. They should be able to go to a place to do drugs where they are protected while they're going through the drug trip. But you shouldn't let them on the street. They're a danger to themselves and others.
The active ingredient is a drug called 2CB, which is often shortened on the street to the term 2C. The drug was first synthesized in 1974 and was initially used in conjunction with psychotherapy to treat mental disorders. Later, the drug became illegal in the United States. These days, the drug is popular on the party scene as a substitute for ecstasy. Although often referred to as pink cocaine, strictly speaking, 2CB should not actually contain any cocaine. As is the case with many illegal drugs, the formulation of the drug is not consistent. People who manufacture and distribute substances often find creative ways to mix them based on the availability of chemicals and with profit in mind. Sometimes pink cocaine is nothing more than a mixture of drugs like ketamine, ecstasy, and, on rare occasion, cocaine. It is not even 2CB at all. The quality.
There's no difference, as far as I'm concerned, between coffee, alcohol, tobacco, and cocaine or heroin. It's all the same. There's no reason for the government to be involved.
Control instituted by drug dealers is nothing short of criminal.
But we should be using more automatic, like driverless cars. Our cars at this point should be driverless because driverless cars are safer than human cars.
Criminal. 2CB can cause hallucinations, increased empathy, euphoria, and a sense that colors and patterns are enhanced. It also causes anxiety, nausea, vomiting, dizziness, sweating, confusion, paranoia, loss of concentration, giggling, spasms, intestinal discomfort, and an increased heart rate. The effect of the drug usually lasts for between 4 and 12 hours. 2CB sounds like the perfect addition to any party as long as people want to vomit in a state of confusion while sweating profusely. Moving back to the story of Macy Lathers, when she said that she took pink cocaine, there's no way to know what she actually had in her system without testing. It's likely what she consumed was simply a mixture of ketamine and ecstasy. And combining her statements with the fact that she was vomiting, it is reasonable to believe that she was significantly impaired by her drug use. In addition, Macy told the authorities that she came from the future, had a crystal ball, and aliens were coming. There's not much question as to her guilt. I think Macy will probably be convicted of 2 counts of DUI manslaughter as well.
Guilty of what? Guilty of what? I mean, she was not functional when she stepped into her car. Like, if she would have had sex with someone, it would have been rape. So she's impaired. She has no judgment. But you are going to hold her liable for choosing to step into a car? That doesn't make any sense.
All those other charges, unless the state offers her some type of plea bargain. In the state of Florida, DUI manslaughter is a second-degree felony that is punishable by 4 to 15 years in prison. Therefore, Macy is facing 8 to 30 years in prison, not counting any of the other charges. In addition to a magical prison journey, her driver's license may be permanently revoked. I think this would be a good idea. What do I think happened in this case? This is just a theory, my opinion. Macy Lathers was self-centered, impulsive, immature, hedonistic, grandiose, shallow, failed to regulate her intake of substances, falsely believed she was special, and had a sense of entitlement. Her personality traits meant that she was well qualified to be an Instagram model.
I don't know if any of this is true. I mean, just because a person is drugged and steps into their own car, I mean, this could happen to anyone. I mean, she chose to take drugs. Yeah, that's it. Well, once a person chooses to take drugs, then whatever lack of judgment they have, that's already because they took drugs. So you can accuse her of taking drugs and hold her liable for any decision she made thereafter.
Model. It's not clear how Macy made a living, but she had access to a luxury car and plenty of drugs. For some reason, her license was suspended, which usually doesn't happen by accident. It stands to reason that Macy did something which caused this to happen. Perhaps she did not abide by all the traffic laws. Whatever the reason for the suspension, Macy was well aware that she was not allowed to drive. Instead of following the law, Macy invested in her belief that she was an amazing person and should not be subject to
Right. Why was she driving while suspended? That's not good.
societal norms. Furthermore, she felt entitled to take illegal substances. On the day of the fatal collision, Macy was impaired and drove through a red light at 78 miles per hour. There's no information available about a catalyst for this behavior, like a relationship gone bad or an argument. Maybe this was just a regular day. Macy just didn't care at all. She had a reckless disregard for the safety of others. After killing 2 people in the collision, Macy's first thought was to escape responsibility. She walked along North Miami Avenue with her hood pulled up to conceal her identity. For some reason,
You see, she's not pretty. She doesn't have a good body.
people in the collision, Macy's first thought was to escape responsibility. She walked along North Miami Avenue with
She doesn't have a good body. She's short and fat.
her hood pulled up to conceal her identity. For some reason, perhaps due to an interaction with bystanders, Macy returned to the scene of the collision and was arrested. She probably did believe that she was from the future and aliens were on the way, which indicates a disconnect from reality. Despite this, Macy was thinking clearly enough to flee the scene. What would justice look like in this case? These cases are so challenging.
She did not think clearly enough to flee the scene because she walked right back.
As far as arriving at any type of fair
I mean, if she would have fled the scene and then disappear for a day or two, it's going to be hard to prove her guilt, and then she could have gotten a plea.
There's no way to know what should be done without learning more about Macy's background. It is possible that Macy was drugged without her knowledge. Maybe she was running from somebody. There are all kinds of possible explanations for her behavior, which could mitigate or even eliminate her culpability. Based on the information available right now,
Okay. Oh, this is interesting.
Hi everyone, this is Professor N does Science, and today I want to talk about angular momentum in another one of our videos on rigorous quantum mechanics. If you have studied classical mechanics, you will know that angular momentum is a key concept to understand the physics of many systems, so it won't come as a surprise that the same is true for quantum mechanics. For example, angular momentum is absolutely essential to understand the motion of particles in central potentials, an example of which is the all-important hydrogen atom. But angular momentum in quantum mechanics is a lot more general than what you might suspect from classical physics. You might have heard about the spin of quantum particles. Spin is actually just another type of angular momentum. So what we will do today is to motivate the concept of angular momentum in quantum mechanics, and we will also explore how we can generalize these ideas, which will prove really important as we move forward. So let's go. We're going to start with a reminder of angular momentum in classical mechanics. So let's consider some reference point, and for ease of visualization, let's also draw a vertical axis going through that point precisely. If we have a particle here at position r that is moving with momentum p, and again, for ease of visualization, we can imagine that it is going around the reference point in a circle, then the angular momentum vector L is the cross product between the position vector r from that reference point and the linear momentum p. And this definition is general, so you should view this drawing as simply an example for clarity. Angular momentum, like position and linear momentum, is a vector quantity, and this means that for calculations, we typically want to write it in terms of components defined with respect to some basis. For example, in Cartesian coordinates, the components would be Lx, Ly, and Lz. But moving forward, we're going to be more general and write these as L1, L2, and L3. We will use the same convention for the position vector, typically given as x, y, z, but we will label them R1, R2, and R3. And similarly for the linear momentum vector. In this notation, we can now carry out this cross product, and we find that L1 is equal to R2P3 minus R3P2, and similarly for the other two components. So what is angular momentum in quantum mechanics? Angular momentum is described by an observable L hat.
R2P3 minus R3P2? Why is that? Where's this from? What is going on? My God. Essential quantum mechanics clearly explained simple.
Hello, and welcome to another episode of Mastering Quantum Mechanics Through Problems. My name is Dr. Jacob Hewis. In this presentation, I will solve a good problem that helps to understand some key operations in quantum mechanics, including finding the expectation values of position, momentum, and energy. To begin, I present the solutions to an infinite square well potential. This was solved in a previous video, and the link to that video will be in the description. Each wave function phi sub n depends on the quantum number n.
Okay, we want the wave equation.
Hello. The topic for today's video is the discovery of proton and neutron. We have studied in the previous videos about the discovery of an atom, and then how J.J. Thomson discovered the presence of a subatomic particle that was an
Terrible audio. Okay, let's look for the wave equation. With the imaginary, let's see if complex numbers, yeah, complex solution. Complex numbers and quantum mechanics. No, I don't want that. Why momentum in quantum physics is complex. Schrödinger equation, get the deepest. No, I just want a normal wave, a classical wave equation. Just classical wave equation. Classical wave equation. I'm looking to see. I don't see I. Mechanical, the wave equation, one-dimensional, 7.5 minutes.
Welcome to Lecture Online, and now for something a little bit more complicated, a little bit more advanced, the standard wave equation, but we're only doing it in one dimension. And this is it. Okay, now what does that really mean? We have the partial second derivative of the wave function y with respect to position equals 1 over the velocity of the wave squared times the partial second derivative of the wave function y with respect to time. What does that even mean? Well, that is what we call the standard wave equation. So we can do that in 1 or 2 or 3 dimensions, but it describes a wave moving out with oscillatory motion either in 1 dimension, in planar dimension, or in three dimensions. So we're just going to take the 1 dimension case. What that means is if you take the wave function, or what you think is a wave function, and of course by now we know this is indeed a wave function, if you plug that in here and then go through this process and the left side equals the right side, we are indeed dealing with a wave equation. So that means that this will indeed be a wave equation, or equation representing a wave. All right, let's go through the process and see if that's indeed the case. Now, the first thing we're going to do is take the first derivative with respect to y of y with respect to x of this function right here. So the partial of y with respect to x is equal to. Now, what that means when you take a partial.
But why do you have this equation? What's your starting point? What's wrong with these people? Classical wave equation, separation of variables.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to at OCW.
A couple of things. First of all, last time we talked about the two-slit experiment, and it's mostly classical. There's only a little bit of quantum in it where we talk about momentum as being determined by h over lambda. Okay, but what were the two surprising things about the two-slit experiment? There are two of them. Two surprises. Yes. Yes, that's the most surprising thing, and that when you go to really low intensity, so there's only one photon, which is quantum, in the apparatus, somehow it knows enough to interfere with itself, and this is the most mysterious aspect. But then there's one other aspect, which is how it communicates that interference with itself. What is that? You're hot. You want to do another one? What do you mean by how communicates? Well, here we have the screen on which the information is deposited, and you have
it reverts back into a particle.
Possibly, some sort of probability distribution, which is a kind of a continuous thing, but you don't observe that. What do you observe? So you could
a dot.
Say the state of a particle has amplitude everywhere on this screen, but what do you see in the experiment? Yes.
So you just see like one, then you see it at red points, and then thousands and thousands. And then you see it like minutes.
That's exactly right. So the state of the system, which is distributed, collapses to a single point. We say that what we are observing, and this is mysterious and to bother you now, we're seeing an eigenvalue of the measurement operator. So we have this sort of thing, it goes into the measurement operator, and that measurement operator says, this is one of the answers I'm permitted to give you. And another aspect that's really disturbing or puzzling is that you do many identical experiments, and the answer is always different. There's no determinism. It's all probabilistic. So this is really, it should bother you, and eventually it won't. Okay. Now there's another question I have. When I
started listening to his course. It sounds like he would have the best course in quantum mechanics. He's an experimentalist.
The two-slit experiment. I intentionally put something up on the diagram that should have said this is ridiculous. I used a candle in the lecture and I use the light bulb in the notes. Now, why is that ridiculous? Yes.
These have many frequencies.
That's right. So these sources, the sources of light that I misled you with intentionally, have a continuous frequency distribution, and the interference depends on the same frequency. So that the only way you would see any kind of diffraction pattern, any kind of pattern on the two-slit experiment, is if you had monochromatic light. It would all wash out. You'd still get dots.
Oh, that's very interesting. So, in order to have an interference, they have to be of the same frequency.
The dots would never give you anything except perhaps a superposition of 2 or 3 or an infinite number of patterns. Okay, this is, again, something that's really bothersome. Now, I also used the crude illustration of an uncertainty principle, that the uncertainty in position along the z-axis and the uncertainty in the momentum along the z-axis was greater than h. And this, I froze and I didn't realize that I had delta s, the width of the slit, but it really is the same thing as dz, because the slit is how you define the position in the z-axis. And so this is the first taste of the uncertainty principle. And I said I didn't like it. Okay, in quantum mechanics, you're not allowed to look inside small stuff. You're not allowed to see the microscopic structure. You're only able to do experiments, usually thought experiments, an infinite number of identical experiments, and they reveal the structure in some complicated encoded way. And this is really not what the textbooks are about. The textbooks don't tell you how you actually think about a problem in quantum mechanics. They tell you, here are some exactly solved problems. Memorize them. And I don't want to do that. Okay, last part of the introduction here. Suppose we have a circular drum, a square drum, and a rectangular drum. Have you ever seen a square drum or a rectangular drum? Do you have an idea how a square drum would sound? Yes, you do have an idea. It would sound terrible, because the frequencies you get are not integer multiples. It would just sound amazingly terrible. But if you had a square drum or a rectangular drum, you could do an experiment with some kind of acoustic instrument to find out what the frequency distribution is of the noise you make. And you would be able to tell it's not round, it might be square, or it might have a certain ratio of dimensions. This is what we're talking about as far as internal structure is concerned. And it's very much like what you would do as a musician. I mean, when a musical instrument is arranged correctly, it's not like a square drum. It sounds good. And that's because you get harmonics, or you get integer multiples of some standard frequency. Okay, so now we're going to talk about the classical wave equation, which is not quantum mechanics, but it's a very similar sort of equation to the Schrödinger equation. And so the methods for solving this differential equation are on display. And so the tricks is, well, first of all, where does this equation come from? And it's always forces equal to mass times acceleration in disguise. Okay, and then you have tricks for how you solve this. And one of the most frequently used and powerful tricks is separation of variables. You need to know how that works. Then once you've solved the problem, you have the general solution. And you then say, well, okay, for the specific case we have, like a string tied down at both ends, we have boundary conditions. And we impose those boundary conditions. And then we have basically what we call the normal modes of the problem. And then we would ask, okay, well, suppose we're doing a specific experiment or doing a specific preparation of the system. And we can call that the pluck of the system. And you might pluck several normal modes. You get a superposition state. And that superposition state behaves in a dynamical way. And you want to be able to understand that dynamics. And the most important thing that I want you to do is, instead of trying to draw the solutions to a differential equation, which is a mathematical equation, I want you to draw cartoons that embody your understanding of the problem. And I'm going to be trying to do that today. Okay. So in this course, for the first half of the course, most of what we're going to be doing is solving 4 exactly soluble problems: the particle in a box, the harmonic oscillator, the rigid rotor, and the hydrogen atom. With these 4 problems, most of the things that we will encounter in quantum mechanics are somehow related to these. And in the textbooks, they treat these things as sacred, and they say, okay, well, now you solve them, you understand quantum mechanics. But these are really tools for understanding more complicated situations. I mean, you might have a particle box, instead of with a square bottom, it might have a tilted bottom, or it might have a double minimum. But if you understand that, you then can begin to build an understanding of what are the things in the experiment that tell you about these distortions of the standard problem. And the same thing for harmonic oscillator. Almost everything that's vibrating is harmonic approximately, but there's a little bit of distortion as you stretch it more. And again, you can understand how to measure the distortions from harmonicity by understanding the harmonic oscillator. The rotor is all the same. So I would like to tell you that these standard problems are really important, but nothing is like that. And what's important is how it's different from that. And this is my unique perspective, and you won't get that from Macquarie or any textbook. But this is MIT. So they're templates for understanding real quantum mechanical systems.
So far, he is an amazing teacher. This is the second lecture that I'm watching of his in this course. He's absolutely incredible. 1 second, I have a message. Mm-hmm.
And the big thing, the most important technique for doing that is perturbation theory. And you won't get that from Macquarie or any textbook. But this is MIT. So there are templates for understanding real quantum mechanical systems. And the big thing, the most important technique for doing that is perturbation theory. And so perturbation theory is just a way of building beyond the oversimplification. And it's mathematically really ugly, but it's tremendously powerful. And it's where you get insight. Okay, now, many people have complained that they found 561 hard because it's so mathematical. And maybe this is going to be the most mathematical lecture of the course, but I don't want it to be hard. Now, chemists usually derive insights from pictorial rather than mathematical views of a problem. So what are the pictures that describe these differential equations? How do we convert what seems to be just straight mathematics to pictures that mean something to us? And that's my goal, to get you to be drawing freehand pictures that embody the important features of the solutions to the problems. Okay, so we're going to be looking at a differential equation. One of the first questions you ask, well,
I love his approach. Absolutely amazing.
Where did that equation come from? And you're not going to derive a differential equation ever in this course, but you're going to want to think, well, I pretty much understand what's in this differential equation. And then we'll use standard methods for solving that equation.
1 second, message.
And one such differential equation is this. Second derivative of some function with respect to a variable is equal to a constant times that function. Now that you know sines and cosines are solutions to that, and you know that exponentials are solutions to that.
So, I mean, the function is probably, he means y. It looks like force. So this looks like the spring and mass, the acceleration. This is the acceleration of the mass is a constant times its location. This is like the constant of the spring. Shouldn't this be negative? What did he say?
So that is standard methods for solving that equation, and is equal to a constant times that function. Now that you know sines and cosines are solutions to that, and you know that exponentials are solutions to that. Now that pretty much takes you through a lot of problems in quantum mechanics. But now one of the important things is this is a second order differential equation. And that means that there are going to be two linearly independent solutions. And you need to know both of them. I'll talk about this some more later. Now, sometimes the differential equations look much...
Two of them, he said two linearly dependent, two linearly independent.
And you need to know both of them. I'll talk that there are going to be two linearly independent solutions.
So sine, cosine, I guess.
And you need to know both of them. I'll talk about this some more later. Now, sometimes the differential equations look much more complicated than this. And so the goal is usually to rewrite it in a form which corresponds to a differential equation that is well known and solved by mathematicians whose business is doing that. But we won't be doing that. Okay, but usually when you have a differential equation, the function is of more than one variable, and frequently it's position and time. And so the first thing you do is you try to separate variables. And so that's what we're going to do. So we have a differential equation. And the first thing is a general solution. And one of the things that this solution will have is nodes. And the distance between nodes, here's a node, that's half the wavelength. And we know that in quantum mechanics, if you know the wavelength, you know the momentum. And so nodes are really important because it's telling you how fast things are moving. We can also look at the envelope. And this would be some kind of classical as opposed to a quantum mechanical probability distribution. And so it might look like this. But the important thing about the envelope is that it's always positive because it's probability, as opposed to probability amplitudes, which could be positive and negative.
Okay, this is lecture 4, so I skipped too much, so I'm not going to go into this right now. Let's see, the movie, The Humiliated Hollywood, for the environmentalists.
Now, I don't know how things are in your country, but here, a couple of years ago, people were very excited about going electric. Like everything that was working on gas, if you could change it to electric, people would try and do so. And this was actually grassroots. It wasn't because of Greta Thunberg or anything like that. People from Eastern Europe, they're a lot more pragmatic. And what they realized is that the people who actually switched to electric, they were paying a lot less. So everyone thought that it's a good idea. And I'm not going to lie, I was one of them. It wasn't with an electric car, but it was due to the fact that since I'm buying a new house, since I'm making a down payment, might as well get an induction stove and get an electric oven and change as many things as I can to electricity. Now, like many other people, myself have also discovered the downsides of doing this because the media wouldn't tell you. And it's something that you probably wouldn't find out unless you're doing it yourself. Because even with research, most of this stuff doesn't come up on Google. So the moment I found out that going fully electric is bad was after I bought the house. I had my parents and my relative coming over, and we were doing spring cleaning, and we were getting ready for setting up a big feast. So the induction stove was working, the oven was working, the television was working, and the computer, as well as the washing machine. And guess what happens? All of a sudden, power outage. Massive. And you're like, whoa, like what happened? Because you know that the electrical system is new, you know that everything is supposed to work fine. It's like, why is it doing this? So, we restarted, we fixed the problem, and then we put everything back in place, and then power outage. So we discovered that, it's not a good idea to actually run the electric oven simultaneously with the induction stove, simultaneously with the washing machine. It was just basically like too high demand of power. Now, I don't know if this happens everywhere, but take into account that my place was pretty new. So they didn't do a bad job with electricity. In fact, like the electricity doesn't go down for this reason, unless like I actually plug everything and I run everything. But take into account that there are other places, especially in Europe, that are very old.
But it sounds like the issue was in your apartment. So your apartment didn't allow for multiple things to run simultaneously.
And they were built in mind with the fact that the person may need a lighting bulb, a television, and a refrigerator, and that's it. So the more you add, the more you diversify your energy, the more likely it is that what happened to me would happen to them. Now, apparently there are ways around this, like you can pay the electric company more and they can do some, I don't know, technological stuff in order to get your house. But now you're paying extra. And the whole reason that people are going electric is to pay less. So this was like number one, the first issue. The second issue has to do with the Ukrainian conflict. Like all of a sudden, electricity prices are spiking. So the idea that electricity is cheaper, well, the more people that go electric, apparently the supply and demand exists. Like we still live in a capitalist society. And the price of electricity just goes up and up and up. So the idea that, you're going to electricity and it's convenient, well, now it seems people aren't so sure anymore. They generally don't know. And finally, it's the issue of convenience. Now here in Germany, and this is what actually got me started, is the fact that electric vehicle sales are dropping. And in the European Union, in some cases, the EU is actually trying to use taxpayer money in order to make these things cheaper, to subsidize, right? I don't know if it's the auto industry itself, but like they're doing it for...
Okay, I don't know what he's talking about. Potassium? What is that? What are we looking at? Orbitals of the potassium atom. Let's look again. For the classical wave equation with a complex solution. The complex notation, that's what we want.
Hi, this is Jonathan Gardner, continuing from the previous video. We talked about some terminology about the different variables that are associated with wave functions, with sinusoidal waves. Now we're going to rewrite this in complex notation, and I surely hope that this is not new for you. If this is unfamiliar for you, if this is new, then you need to go study complex numbers. And the good news is you should be able to pick it up in about a week and understand everything that works. The bad news is there's some details that you're going to miss that become important. So you're going to want to study complex numbers until you get super comfortable and you understand the edge cases and everything like that. So Euler's equation could be rewritten, Euler's formula can be rewritten this way. Okay, so e raised to an imaginary power is basically cosine minus the imaginary the sine of the number that you have there. So this is a complex number. You have a real and a complex part. The complex part is not imaginary. The imaginary part is not an imaginary number. The imaginary part is sine theta. So you can rewrite your function f of x comma t as the real. You want to see cosine theta. So we just take of a e to the I times kappa x minus omega t, and omega is kappa times the frequency plus our delta. Okay. And that will give you the same function. Okay. And the beauty of this is now you don't have to worry about what's cosine times cosine or like that. You can just do straight multiplication using how you know how powers interact with each other.
That's too fast. I need something much slower.
This video is designed to go over complex numbers, a review, I anticipate for most of you, and also working with waves in 3 dimensions to expand on what we did last time. So we're going to talk first about how we use complex numbers in both the Cartesian form and the polar form, and in particular, I'll emphasize the polar form of complex numbers, and we'll look at finding the real and imaginary parts of the number. Then we'll talk about how to find speed, frequency, wavelength from a harmonic function of a wave, as we started last time, and we'll emphasize looking at spherical and cylindrical waves and plane waves in 3 dimensions, and the 3D-dimensional wave equation. So the complex plane is a great place. The complex plane plots relevant physical quantities or real quantities on the x-axis. That's things like displacement. If you were looking at the actual physical displacement of an object, it would be plotted on the x-axis. On the y-axis, we plot the imaginary quantities or the non-physical quantities, such as phase. And the imaginary values are written or drawn as a displacement along the y-axis. So this is where our letter I, our symbol I, is used to define displacement along the y-axis. And yes, you'll know that I is in fact the square root of -1, which we'll get back to. So this is our basic complex plane with real values along the x-axis and imaginary values along the y-axis. We'll be drawing our vector z in the complex plane. So here we've got our complex plane again, and our any vector z can be drawn in this complex plane. The magnitude of z is the red bar, and we can write this as x plus I, y. So it's like writing a vector where we would use the vector components x and y, except here we have the I in addition to tell us that we need to plot it along the y-axis. Now take a look and you'll see that the x variable is actually equal to r cosine theta, and the y variable is equal to r sine theta. So our complex number now has an x component and a y component, and we want to be able to use these components to define both the magnitude of the vector and the direction of the vector, or this angle theta, in our complex plane. If we start with our complex number z equals x plus iy, we also remember that the complex conjugate for a complex number is z star, and for the complex conjugate we simply negate or invert any imaginary components, in this case it's x minus iy. And the magnitude of a complex number is actually defined as, we write it with those two bars, that z magnitude is defined as the square root of z times its complex conjugate. What you'll see if you multiply that out is that you have simply the square root of x squared plus y squared. And that's what you expected from looking at this picture of x and y, and this makes a right triangle. You would expect that x squared plus y squared should equal z squared, or the magnitude is the square root of x plus y squared. Now, how about the angle? The direction of our vector, defined relative to the positive real axis, is the inverse tangent of y over x. Again, as you would expect from the angle as it's drawn here, and y over x, or the inverse tangent of y over x, giving us that angle.
Wait, what is theta? It's the inverse tan of y over x. Y over x. But what is the angle theta? I don't get it.
From the or the magnitude is the square root of x squared plus y squared. Now, how about the angle? The direction of our vector, defined relative to the positive real axis, is the inverse tangent of y over x. Again, as you would expect from the angle as it's drawn here, and y over x.
Y over x. What is theta? Is theta between... Wait, what's going on? I don't know what theta is. Why is it inverse tan y over x? I don't get it. Y over x. Like y over z is sine, x to z is cosine, no? Or is it hypotenuse over? I don't remember. I don't remember my trigonometry.
X, or the inverse tangent of y over x, giving us that angle. So this letter I, the symbol I that we use all the time. Well, I is actually in the complex plane. I is a counterclockwise rotation of pi over 2 or 90 degrees. So let's look at an example. Suppose that b is along the x-axis as it's drawn here in red. Well, if we multiply by I, so now we have our quantity I times b. Look, now we have an imaginary number of length b that's along the imaginary axis. So we draw it as I've drawn it in the picture here. And what it is this vector b rotated by 90 degrees, rotated by pi over 2. And if you try this starting at any position, you'll see that what I does, multiplying by I, is it actually rotates your vector by 90 degrees. Kind of a fun little thing here.
No, it doesn't, because if your vector starts as imaginary and you multiply it by I, it remains in the same direction, no? Which picture best represents... Which picture best represents I squared b in the complex plane? I don't even know what that means. I squared just means negative b. Negative b in the complex plane. Complex plane is this. Negative b. I would say it's this.
Just a couple of experiments or examples dealing with imaginary vectors and the complex numbers and the imaginary symbol I. So with anything where we have choices and I'm asking a question, what I expect you to do is to pause for a moment to come up with the answer, and I will go ahead and show the answer. But you can pause the video here before seeing the answer. So which of these pictures represents I squared b in the complex plane? You can pause here. And what you'll see is that I squared times b would be a rotation of b by 90 degrees. And then, in other words, b being just a positive value magnitude b, rotation by 90 degrees, rotation by 90 degrees again, and we get a line in this direction. Another way of thinking about this is looking at how do we write I squared b in this complex plane. So pause here.
B, it's negative b.
And yes, after you think about it, we see that I squared is simply minus 1. So it becomes minus b. And if you look back at this picture, minus b would be along the real axis in the minus b direction. All right, so a nice result of this is that I squared b now equals minus b, and I squared then equals minus 1, I equals square root of minus 1, and we knew all that already. Couple review questions.
The expression 1 over I is equivalent to... So 1 over I, you can multiply both top and bottom by I. So the top becomes I, and the bottom becomes negative 1. So it's just negative I. Negative I is D.
So the expression 1 over I is equivalent to which? Pause here. And you'll see that the expression 1 over I, this is a little bit of a tricky one, is equal to minus I. You can prove that to yourself by multiplying by I over I, and you will get minus I. What about the expression minus I over I? Pause.
Minus I over I. Wow, I don't know. Maybe multiply by I top and bottom. The top becomes -1 times -1 is positive. It's -1. It's B.
And you see that this is, in fact, -1. There is nothing particularly magical about that. It's simply -1. But you can prove it by multiplying by I over I, or just dividing through by I. Okay, so we're going to take a little segue here with that introduction to the polar and Cartesian form, the polar form of complex numbers, and talk about Euler's theorem. And the way we get to Euler's theorem is actually by doing a Taylor series. I'm not going to do the Taylor series just as a little for note, but I will show you how you would use it. So the Taylor series is defined like this. It's a function that's a series. And the Maclaurin series is a particular Taylor series expanded around a equals 0. So rather than expanding around a general A, you expand around a equals 0. And that looks like this, where your function now, instead of having a's in it, we put in zeros. Now, to get to Euler's theorem, what we do is we write the Maclaurin series for each of the following expressions: cosine theta, sine theta, and e to the I theta. So write all those out with...
What is segue? Taylor series. Go understand Euler's theorem. Taylor series expanded around A. So f of x is the sum of x minus a to the n over n factorial times f to the n of a. So whenever you have something of this form, you can expand it to f of a, first order, plus x minus a times derivative. I remember deriving this when I was little. F prime of a plus x minus a squared over 2 factorial times f. Is this f to the n? This is the nth power? So where's n? F a, x minus a plus... Where's n? I don't get it. This is Taylor. F of x is the sum of... Given that it's the sum of x minus a to the n. Oh, you sum it, she didn't say, from 1 to n. So n is the counter. They usually say I. They don't say n. Jesus. Okay. So from 1 to n, is f of a plus x minus a times f prime of a. So if you want to add all these terms, f to the first, f to the second, f to the third, I guess. I don't know. I don't remember Taylor. I don't even know what's going on here. Maclaurin series, a equals... this is too much. Too much. Complex sinusoid.
Complex sinusoids are an important part of signal processing, and we can define a complex sinusoid, x of t, with amplitude a and frequency omega naught and phase phi. This is I've written here. We've got a e to the j omega naught t plus phi. Now we recall that the Euler identity, which says that r e to the j theta can be expressed as r cosine theta plus j times r sine theta. And applying this to our newly defined complex sinusoid, we see that the complex sinusoid actually consists of a cosine and a sine term. So I can write this as a cosine of omega naught t plus phi plus j.
I need to go through this step by step. I'm skipping too much. Complex exponential representation.
Okay, in this video, I'm going to continue on with my tutorials bringing us from electromagnetism to optics. This is video number 6, and I'm going to discuss the complex wave functions. The previous videos to this which are relevant, number 5, were discussed complex numbers, and 4 were discussed waves. So as a quick bit of revision, we saw that we can describe waves generally using sinusoids or harmonic functions. The sinusoids are cosine and sine. Now, there are lots of other sorts of waves. For example, we could have Gaussians, but we're not going to discuss Gaussians at the moment. We're just going to talk about harmonic waves or sinusoids. And we saw is, using these, we can write any wave function as the amplitude A outside of cos of kx plus or minus omega t plus or minus delta. So we get the following. Where we know that the phase shift is delta, omega is the angular frequency, and k is the wave number. So in the previous video, I showed that k is equal to 2 pi over lambda. We showed that the temporal period, tau, is equal to 1 over the frequency, nu. And we saw that the angular frequency, omega, is equal to 2 pi times the linear frequency, nu, like that. We saw all of this in the past. Delta then is just a phase shift. Now, I said in a previous video that we can use cosine or sine, that it didn't matter. The only difference between them was that there was the phase shift. But yet, even here, I'm writing cosine. Why am I writing cosine? Why not pick sine? And I'll tell you that now in a moment. So we know at this stage that complex numbers are, we know the complex numbers can be written as follows, right? So we have, using Euler's formula, we have e to the I theta is cos theta plus I times sine theta. And the reason this is important is because either of these, this cos or this...
And how do we know this? This is Euler's formula? I need to be able to...
Well, we know the complex numbers can be written as follows, right? So we have, using Euler's formula, we have e to the I theta is cos theta plus I times sine theta. And the reason this is important is because either of these, this cos or this sine, they're basically harmonic functions, okay? Which means they can be used to describe a wave function. So what this kind of suggests is that somehow we can use this Euler's formula in order to describe a harmonic function if we, I suppose, accept that we take either the real part here or the imaginary part, because either the sine or the cosine can be used. So for example, let's say that I write RE, and that means real. So I take the real part of e to the I theta, and that will give us, of course, cosine theta. Similarly, if I ask for the imaginary component, I'm simply going to get sine of theta. So both of these are harmonic functions. So what this means is that I can actually use my complex representation and use e to the I theta, provided I know that when I actually want to do some calculations, I must either take the real component or I must take the imaginary component and not both. So it is customary for us to use the complex representation and assume that the wave function is actually the real component of it. And that's why we use cosine, because cosine is the real component of your complex wave function. So just to show you different ways of writing this, we know that any complex number can be written as the real plus I times the imaginary part. Now, using the complex conjugate, we can rewrite these as follows. The real part can be written as 1/2 outside of z plus z star, and the imaginary can be written as 1/2i outside of z minus z star. Okay, where did we get these?
I need to, from the previous lecture.
The reason we got these was because we saw in a previous video how to get cosine and sine. We know that cos is equal to e to the I theta.
Okay, I need to go watch the previous video. Where's the previous video? The previous... How many videos? 735 videos. Jesus, I'm never going to find it. So we need just complex numbers, I guess. Oh, EM to optics 5, it should be. Here's EM to optics 7. Where's EM to optics 5? This is the whole thing.
Okay, in this video, I'm going to begin a series of tutorials going from, or taking us from, electromagnetism to optics. And in this particular video, I'm going to try and motivate the whole topic. Now, why do I think this is important? Most university students will begin a course in optics somewhere in their first or second year in university. It'll usually start with a course in geometric optics and perhaps also taking elements of wave optics. Now, once we begin doing wave optics, things they get reasonably complex. However, the foundations for optics will not have been covered because people do not do courses in electromagnetism until at least their second year in university. And why is this observation important? Well, because electromagnetism is the foundation of optics. So without electromagnetism, we do not have optics, and the converse does not hold true. Now, in order to do a beginner's course in optics, you do not need to be very proficient in classical electromagnetism. What you do need to do is to look at the results from electromagnetism, take the results, take the predictions, and move forward. So in one sense, you can kind of forget that electromagnetism is the foundation of optics. But this should make sense to you because think about your computer. In order to I don't know, let's say write a piece of code or write a program on your computer. In theory, you could write that piece of code by just looking at the atoms and the molecules in the computer itself. But that's very difficult. So in order for us to build hardware, what we do is we come up with electronics. So we assume that the chemistry and the physics underlying the... Okay, in this video, I'm going to continue on with my tutorials, moving us from electromagnetism to optics. This is video number 5, and I'm going to discuss complex numbers. So the previous videos to this which are relevant are actually not in the section of electromagnetism to optics. I did 4 videos.
I'm going to go get a drink. This is so boring. Oh my God. Oh my God, this is so boring. Okay, you know what? Maybe I'll stop here. We'll continue next time. How long? Yeah, 2 hours is enough. Is it? No, I'm just gonna pause it.
That's bad. And the question has to be why? Why is it bad? And here you have an example, like everything that Hollywood is making right now. I would say like 80%.
Where were we?
Videos entitled complex numbers, and hopefully I have all that you need to know in those videos. So what I'm going to do in this particular video is to summarize all of that as quickly as I can. If you're not following it, move back to my videos on complex numbers where I've done everything in detail. And I motivated in video 1, I introduced it in video 2, did a lot of work in video 3, and closed it up in video 4. Okay, so specifically I suppose video 3 is the more is the longest of the lot. Okay, so let's start talking about complex numbers. So on the number line, we know that we have the numbers, we have the negative numbers, we have 0, and then of course we have the positive numbers. Okay, I've left out -1 and 1. But what we also have there are the rational numbers like pi, like e, and 0.5. So with these numbers, we can almost do everything. We can do addition, subtraction, multiplication, and division. What we cannot do are get the square roots of negative numbers. So we define the Greek letter iota as the square root of -1. And I motivated in video 1 of my videos on complex numbers. I showed you why we need to discuss this. So now we know that iota or square root of -1 is different. So what we come up with are things called Argand diagrams, where we draw the complex or the square roots or complex numbers perpendicular to the normal number line. So this is the normal number line here from -infinity to +infinity. And then we draw perpendicular to it our imaginary numbers. And now we go from an infinite number line to an infinite number plane. So in general, we call the imaginary number as z is equal to x plus I times y. Okay, now because we can draw it like this, we're able to do a small bit of trigonometry and invoke the angle theta. So if we invoke the angle theta, we're able to rewrite, and let's say the magnitude of the length of this is a, we can rewrite the complex number z as a outside of cos theta plus I times sin theta. Why this is important is because cos theta plus I times sin theta is actually part of Euler's formula. This is e to the I theta. So we can rewrite all our complex numbers as a outside of e to the I theta. Now, the next thing we need to do is our complex conjugates. So that is z star. And what we do is we swap the sign or change the sign in the
Okay, so that's where it comes from. So z is equal to x plus iy. X is cosine theta. Y is I sine theta. And A is the multiplier. But why is cosine theta plus I sine theta e to the I theta?
theta. So if we invoke the angle theta, we're able to rewrite, and let's say the magnitude of the length of this is a, we can rewrite the complex number z as a outside of cos theta plus I times sin theta.
So far, so good.
Why this is important is because cos theta plus I times sin theta is actually part of Euler's formula. This is e to the I theta.
Okay. We need Euler's formula.
Okay, in this video, I'm going to begin a series of tutorials going from, or taking us from, electromagnetism to optics. And in this particular video, I'm going to try and motivate the whole topic. Now, why do I think this is important? Most university students will begin a course in optics somewhere in the first or second year in university. It'll usually start with a course in geometric optics and perhaps also take in elements of wave optics. Now, once we begin doing wave optics, things get, they get reasonably complex. However, the foundations for optics will not have been covered because people do not do courses in electromagnetism until at least their second year in university. And why is this observation important? Well, because electromagnetism is the foundation of optics. So without electromagnetism, we do not have optics, and the converse does not hold true. Now, in order to do a beginner's course in optics, you do not need to be very proficient in classical electromagnetism. What you do need to do is to look at the results from electromagnetism, take the results, take the predictions, and move forward. So in one sense, you can kind of forget that electromagnetism is the foundation of optics. And this should make sense to you because think about your computer. In order to I don't know, let's say write a piece of code or write a program on your computer. In theory, you could write that piece of code by just looking at the atoms and the molecules in the computer itself. But that's very difficult. So in order for us to build hardware, what we do is we came up with electronics. So we assume that the chemistry and the physics underlying the atoms and the electrons works, and we came up with electronics to make it easier and quicker to do it. And then when we started building complex devices, we found that even doing it this way was very difficult. So we came up with things called computer programs. So we could technically, of course, write a computer program by just looking at the atoms, but we don't do that. And so each time that you get a new level of complexity, you kind of forget or accept the previous knowledge, which now is just so difficult and cumbersome for you to work with, and you simplify it and use something else. So in theory, you could do all of your optics by just looking at Maxwell's equations, which are from electromagnetism. But of course, we don't do that because it would be very cumbersome. So in these series of videos, what I'm going to discuss are some of the things I'm going to discuss are written in front of you. But first of all, I'm going to discuss waves. So we're going to be talking about wave optics. So this is very important. I'm going to discuss where you get something looking like this. Why do we use x plus or minus pt? I'll discuss that in video number 2. I'm going to discuss the wave equation, sinusoids, complex exponentials. Why do we use complex exponentials instead of the sinusoids themselves? and I'm going to discuss the wave function, which is a solution to the wave equation. And all of this, of course, it falls out from Maxwell's equation. So I'm going to Okay, in this video, I'm going to continue on with my tutorials, moving us from electromagnetism to optics. This is video number 5, and I'm going to discuss complex numbers. So the previous videos to this which are relevant are actually not in the section of electromagnetism to optics. I did 4 videos entitled complex numbers, and hopefully I have all the... Okay, in this video, I'm going to begin a series of tutorials going from, or taking...
But he didn't do... He did not explain Euler's formula, so we need to look it up separately.
Logarithms, where the application of imaginary numbers. There's this really beautiful idea in math that many of the equations and graphs we spend our time with are just shadows of a more elegant, powerful, and higher dimensional mathematics. This higher dimensional mathematics has everything to do with the imaginary number I, the square root of -1. Extending polynomials like x squared plus 1 to include imaginary numbers is relatively straightforward, but there's one pair of functions, exponentials and logarithms, where the application of imaginary numbers is far less clear. 2 to the power of 3 means we should multiply 2 by itself 3 times. But what could it possibly mean to raise 2 to the power of the square root of -1? In the early 1700s, disagreements over these questions threatened the very foundations of mathematical analysis, until Leonard Euler stepped in with a solution so surprising and elegant that it's often called the most beautiful equation in math. This video is sponsored by me. I've written a whole book on imaginary numbers. It's coming out later this year. You can pre-order a copy using the link in the description below. On March 16, 1712, Gottfried Wilhelm Leibniz, co-founder of calculus, sent this letter to the mathematician Johann Bernoulli.
One month ago.
Where he claimed that it was impossible to take a logarithm of a negative number. As Leibniz would detail in a later letter to Bernoulli, logs are just another way to write exponents, and simply don't make sense for negatives. Log base 2 of 8 is 3, because 2 to the third power is 8. Log base 2 of 1 is 0, because 2 to the power of 0 is 1. The reason 2 to the 0 is 1, and not 0 or something else, is that this definition preserves an important property of exponents and logarithms. When we multiply two terms with the same base, their powers add. 2 squared times 2 cubed results in 5 total multiplications of 2, or 2 to the 5th. Defining 2 to the 0 as 1 preserves this property. 2 to the 3 plus 0 equals 2 to the third times 2 to the 0, if and only if we define 2 to the 0 as 1. As we'll see, finding mathematically consistent ways to handle logs and powers of various types of numbers is critical to making sense of Euler's approach. Finding a sensible definition for logarithms of fractions between 0 and 1 is also relatively straightforward. Dividing exponential terms with the same base is equivalent to subtracting their exponents. 2 cubed divided by 2 squared is equal to 2 to the 3 minus 2. This means that 2 to the minus 2 on its own must equal 1 over 2 squared. This is how we arrive at the logarithms of fractions. The log base 2 of 1/4 is equal to -2, because 2 to the -2 is 1/4. Note that we've broken away from the simple definition of integer exponents, where an exponent of n means we multiply a number by itself n times. This doesn't make sense for negative exponents. However, our fractional definition nicely preserves our properties, and when we plot the value of log base 2 for numbers greater than 1 for 1 and for fractions, we get a nice continuous curve. Now, when we finally reach the logarithms of negatives, as Leibniz claims, we basically run out of options. What power of 2 would result in -1? Clearly, positive numbers 0 and negatives will not work. In a response letter a few weeks later, Bernoulli flatly rejects Leibniz's claim. Bernoulli argues that since the derivatives of log x and log of negative x both evaluate to 1 over x, log of x and log of negative x are equal. This would mean that the log function wasn't just one curve, but actually had a positive and negative branch that are symmetric across the y-axis. And the log of -1 just equals the log of 1, so 0. Leibniz was not convinced, and the mathematicians went back and forth for over a year without making progress towards a meaningful resolution. When Leonard Euler, a student of Bernoulli, picked up this still unresolved problem a few decades later, he wrote that not finding a reconciliation would be an indelible stain on analysis. At this point, calculus and analysis were still only 5 or 6 decades old, and relied on some serious hand-waving to handle the infinitely large and infinitely small quantities required. Euler speculated that other mathematicians had encountered the same difficulties with logarithms, but had not published out of fear of breaking this new branch of math without being able to fix it. In an incredible 13-page paper written in 1747, Euler points out logical flaws with the solutions of both Bernoulli and Leibniz, and lays out an unbelievably elegant solution that remains largely unchanged today. First, Euler demolishes his teacher Bernoulli's theory that log of x equals log of negative x. Euler argues that just because log x and log of negative x have the same derivative, this does not mean that the functions themselves are equal. The same faulty logic can be used to show that log of 2x equals log of x, which is clearly false. From here, Euler draws on an example from Bernoulli himself to show that Leibniz is partially correct. In 1702, while investigating the areas of sectors of circles, Bernoulli got stuck on this difficult integral that computes the area of a sector as a function of the position xy on the corner of the sector. Bernoulli realized that if he effectively pulled a square root of -1 out of his expression, he was able to evaluate the integral. The result is a fairly complex expression for the area of the sector, involving I and a logarithm. Euler showed that if he chose the point xy to be 0, 1, Bernoulli's equation would simplify into the logarithm of -1 divided by 4i. Euler argued that since the area of the sector was clearly a real quantity, that the I in the denominator would have to cancel with an I in the numerator, meaning that the log of -1 had to be imaginary. However, just declaring that logarithms of negative numbers are imaginary does not fix the problem, and as Euler goes on to show, it leads to a new set of contradictions. A key property of logarithms is that raising the argument of a logarithm to a power is equivalent to multiplying the logarithm by the power. The log of 2 cubed is equal to 3 times the log of 2. Having established that the logarithm of -1 is imaginary, we can write log of -1 equals b times I, where b is some real number multiple of I. Euler then considered the case where the -1 inside the logarithm is raised to the power of 2. Applying our property, this should be equal to 2 times the logarithm of -1, or 2bi. However, since -1 squared is just 1, and we know that the logarithm of 1 is 0, it also appears that the log of -1 squared is equal to 0, which we just showed cannot be the case. Euler was stumped. Fully appreciating that the foundations of calculus were at stake, Euler wrote that he was tormented by these difficulties, and that for a long time it seemed impossible to rescue the truth. Finally, Euler found a way forward. What if both answers, 0 and 2bi, were correct? What if logarithms didn't have a single answer, but many, maybe even an infinite number of solutions? To see how this is possible, we need to return to the very first question we considered. What does it mean to raise a number to the power of the square root of -1? Although Euler's solution to this problem is incredibly elegant, his path to the solution is not the most intuitive. Euler put a huge amount of trust into his symbols, and was absolutely masterful at finding creative ways of manipulating equations. Euler's mathematical style, and a general mistrust among mathematicians of imaginary numbers, meant that although Euler's 1747 solution is essentially correct by modern standards, it would take over 50 years, well after Euler's death, to be widely accepted. A key factor to the broader acceptance of Euler's solution was the development of more visual ways of thinking about imaginary numbers. Let's use this more visual, intuitive approach to arrive at Euler's answer, and see how he saved calculus. Imaginary numbers are typically used as parts of complex numbers, which have real and imaginary components, often written as a plus bi. We can visualize complex numbers as points on the complex plane, where the real axis is horizontal and the imaginary axis is vertical. We can multiply complex numbers together using the distributive property, and the product of two complex numbers is generally another complex number. A notable exception is when we multiply a complex number by its conjugate. This just means flipping the sign of the imaginary terms. When we work out the multiplication in this case, the imaginary parts will cancel. Taking the square root of this result gives the distance between the number and the origin on the complex plane, also known as the magnitude of the number. Finally, it's very helpful sometimes to express complex numbers in polar form, where instead of writing the real and imaginary parts, we give the magnitude and the angle measured from the x-axis. Multiplying complex numbers in polar form is particularly useful, because it turns out that all the distributive property algebra is completely equivalent to multiplying together the magnitudes and adding the angles of our numbers. So when we multiply two complex numbers together, their magnitudes multiply and their angles add. Now, returning to our problem of what it means to raise a number to an imaginary power, let's consider 2 to the power of some number b times I. An easy operation we can try right away is multiplying this expression by its complex conjugate, 2 to the minus bi, which should give us the distance squared between the origin and 2bi. Following our additive exponent property, the exponents cancel, and we're left with 2 to the 0 equals 1. This is a powerful result. Since our result is a constant that doesn't depend on b, it means that the magnitude or distance from the origin of 2 to the bi is constant, so 2 to the bi must fall somewhere on a circle of radius 1. Perhaps most surprising here is that unlike functions of real exponents, which grow and grow as their arguments increase, functions with imaginary exponents are completely confined to the unit circle. As we'll see, this has everything to do with Euler's assertion that logarithms have an infinite number of solutions. Now, the missing piece of the puzzle, of course, is where exactly does 2 to the bi fall on the unit circle? We now know that the magnitude of 2 to the bi is 1, but what is its angle? To be more mathematically precise, we're saying that 2 to the bi equals some point on the unit circle. Let's say it's an angle theta. So we can write it as a complex number with cosine theta for the real part and sine theta for the imaginary part. Now, can we figure out how b and theta are connected? If we plug in b equals 1, what happens to theta? If we can figure this out, we will have completely solved our problem. To get to the bottom of this, we need to go one level deeper into how exponential functions really work. As we've seen, it's relatively straightforward to make sense of integer exponents, regardless of if these exponents are positive, 0, or even negative. But what about fractional or decimal exponents? Simple fractional exponents like x to the 1/2 are pretty straightforward. By preserving the property that powers of powers multiply, we can show that x to the 1/2 is equivalent to the square root of x. But what about more complicated powers like 0.587? Sure, you can plug this into your calculator, but how does it really work? The first person to really attack this problem was Henry Briggs in 1617, when constructing his incredibly prolific tables based in logarithms. Briggs found a clever computational approach that works by basically zooming way in on an exponential curve until it looks like a straight line. Starting with an x value of 1, for example, we can zoom into our curve by dividing x by 2 and computing the corresponding y value. In this case, 2 to the power of 1/2 equals the square root of 2, or roughly 1.414. Repeating this operation again to zoom in further, we reach x equals 1/4 and y equals the square root of 2, which is equivalent to the 4th root of 2, or about 1.189. After zooming in more and more, Briggs remarkably took 54 successive square roots to the 33rd decimal place. We reach a tiny neighborhood where 2 to the x is very nearly equal to 1 plus alpha times x. This is the equation for a straight line in this neighborhood with the slope of alpha. Briggs used a slightly different formulation, but in our example here, the slope alpha comes out to about 0.693. So when x is close to 0, 2 to the x is very nearly equal to 1 plus 0.693 times x. We can now use this fact as Briggs did to solve arbitrary logarithm or exponential problems like 2 to the power of 0.587. Taking our x starting value as 0.587, we first map to our tiny neighborhood by either taking successive divisions by 2 as Briggs did, or we can go in one big step. To zoom in by a factor of 1,000, for example, we divide 0.587 by 1,000, so 0.000587. Assuming we made it to our tiny neighborhood, we can now find 2 to the power of 0.000587 using our simple linear formula. So 1 plus 0.693 times 0.000587 gives 1.000406,791. Now that we know 2 to the power of 0.000587, we can zoom back out to get our final answer by raising this result to the power of 1,000, computing about 1.5019. Plugging this problem into a modern calculator gives an answer a little closer to 1.50. Third decimal place. We reach a tiny neighborhood part and sine theta for the imaginary part. Now, can we figure out how b and theta are connected? If we plug in b equals 1, what happens to theta? If we can figure this out, we will have completely solved our problem. To get to the bottom of this, we need to go one level deeper into how exponential functions really work. As we've seen, it's relatively straightforward to make sense of integer exponents, regardless of if these exponents are positive, 0, or even negative. But what about fractional or decimal exponents? Simple fractional exponents like x to the 1/2 are pretty straightforward. By preserving the property that powers of powers multiply, we can show that x to the 1/2 is equivalent to the square root of x. But what about more complicated powers like 0.587? Sure, you can plug this into your calculator, but how does it really work? The first person to really attack this problem was Henry Briggs in 1617, when constructing his incredibly prolific tables based in logarithms. Briggs found a clever computational approach that works by basically zooming way in on an exponential curve until it looks like a straight line. Starting with an x value of 1, for example, we can zoom into our curve by dividing x by 2 and computing the corresponding y value. In this case, 2 to the power of 1/2 equals the square root of 2, or roughly 1.414. Repeating this operation again to zoom in further, we reach x equals 1/4 and y equals the square root of 2, which is equivalent to the 4th root of 2, or about 1.189. After zooming in more and more, Briggs remarkably took 54 successive square roots to the 33rd decimal place. We reach a for example, we can zoom into our curve by dividing x by 2 and computing the corresponding y value. In this case, 2 to the power of 1/2 equals the square root of 2, or roughly 1.414. Repeating this.
So how did he calculate it? I don't understand. So he said 2 to the 1/2 is the square root of 2? And this you can find by trial and error.
this operation again to zoom in further, we reach x equals 1/4 and y equals the square root of the square root of 2, which is equivalent to the fourth root of 2, or about 1.189. After zooming in more and more, Briggs remarkably took 54 successive square roots to the 33rd decimal place. We reach a tiny neighborhood where 2 to the x is very nearly equal to 1 plus alpha times x. This is the equation for a straight line in this neighborhood with a slope of alpha. Briggs used a slightly different formulation, but in our example here, the slope alpha comes out to about 0.693. So when x is close to 0, 2 to the x is very nearly equal to 1 plus 0.693 times x. We can now use this fact, as Briggs did, to solve arbitrary logarithm or exponential problems, like 2 to the power of 0.587. Taking our x starting value as 0.587, we first map to our tiny neighborhood by either taking successive divisions by 2 as Briggs did, or we can go in one big step. To zoom in by a factor of 1,000, for example, we divide 0.58 arbitrary logarithm or exponential problems, like 2 to the power of 0.58.
I'm not following. What was his technique? I don't understand.
Taking our x starting value as 0.587, we first map to our tiny neighborhood.
What do you mean you start from 587? How do you do the calculation? You want to get to 2.587. How do you get it?
By either taking successive divisions by 2 as Briggs did, or we can go in one big step. To zoom in by a factor of 1,000, for example, we divide 0.587 by 1,000, so 0.000587. Assuming we made it to our tiny neighborhood, we can now find 2 to the power of 0.000587 using our simple linear formula. So 1 plus 0.693 times 0.000587 gives 1.00406791. Now that we know 2 to the power of 0.000587, we can zoom back out to get our final answer by raising this result to the power of 1,000, computing about 1.50. Plugging this problem into a modern calculator gives an answer a little closer to 1.502. This is just because a factor of 1,000 isn't really zooming in that far. If we zoom in by a factor of 1,000,000 instead, our answers match to the 6th decimal place. We can wrap up what we're doing here nicely into a single equation. 2 to the x approximately equals our linear equation, 1 plus 0.693 times x, divided by our zooming in factor n, all to the power of n to zoom back out. The bigger n is, the more precise our answer is. Injecting a little calculus, 2 to the x is exactly equal to the limit as n approaches infinity of our expression. This is still not quite correct though, because we routed the slope of our line alpha to 0.693. The way this is typically handled is to make the slope term equal to 1 by changing our base. If we define a new variable, x equals z divided by 0.693 and substitute, we're left with a simpler expression on the right and a new base of 2 to the power of 1 over 0.693 on the left. Given more decimals of precision for alpha, our new base evaluates to 2.71828, also known as the mathematical constant e. Putting all this together, we have an equation that is often used as the definition of the exponential function. E to the z equals the limit as n approaches infinity of 1 plus z over n all to the power of n. This equation elegantly describes the zooming in, linearizing, and zooming out procedure that Henry Briggs developed to compute the exponents and logarithms of decimals and fractions. Now that we have a deeper foundation for what an exponential function really is, we're finally ready to make our final attack on imaginary exponents.
So this is the definition of an exponential function. So the definition of e to the z is this, is the limit as n goes to infinity, 1 plus z over n to the n. Limit as n goes to infinity. So this thing becomes 0. But this is bigger, always bigger than 1. Not if it's negative.
Decimals and fractions. Now that we have a deeper foundation for what an exponential function really is, we're finally ready to make our final attack on imaginary.
So what is e to the 0.1? What's the definition of e to the 0.1? Amazing. It's not well defined. We have to define it.
Exponents. The key idea from here on out is figuring out if Briggs' infinite zooming in definition of exponentials works with imaginary numbers. And if so, where on the unit circle a number to a specific imaginary power?
It works for imaginary.
Figuring out if Briggs' infinite zooming in
e to the I is 1 plus I over n to the n as n goes to infinity. So if this is a million, 1 plus square root of negative 1 over n to a million, to a billion, divided by a billion,
definition of exponentials works with imaginary numbers? And if so, where on the unit circle a number to a specific imaginary power will land? So what happens if we plug in the square root of -1 into Briggs' equation? Can we trust the results even though Briggs' equation was derived using real numbers? What does all this mean geometrically? Let's plug in z equals I and temporarily drop the limit and use a smaller value of n, let's say 6. This will reduce the precision of our result, but the intuition should still hold. So we have e to the power of I approximately equals 1 plus I over 6, all to the 6th power. 1 plus I over 6 is not too tricky to think about. It's just a complex number with a real part of 1 and an imaginary part of 1 over 6. Briggs' formula is telling us to multiply this complex number by itself 6 times. Performing the first multiplication, we get
1 plus I over 6 is imaginary. So it's 1 plus I over 6. It's 1/6 of 1. You multiply all these. 1 plus this. So this you ignore, but this you actually look at. So it's 1 minus 1 over 36.
we get 35 over 36 plus I over 3. The polar
Is this so?
formula is telling us to multiply this complex number by itself 6 times. Performing the first multiplication, we get 35 over 36.
1 minus this plus this. It's not ignoring the i's. Okay. It's almost 1. Why is this? Yeah, it's less than 1. But this is here. It's good.
6 plus I over 3. The polar form of complex numbers is helpful here as we continue multiplying. We can write 1 plus I over 6 as a complex number with a magnitude of 1.014 and an angle of 9.46 degrees. Since multiplying complex numbers in polar form is just a matter of multiplying magnitudes and adding angles, we can jump to our final answer by raising 1.014 to the 6th power and multiplying 9.46 degrees by 6, giving a final magnitude of 1.086 and an angle of 56.774 degrees. Note that our answer is not quite on the unit circle as expected, but this is just because we're using a fairly small value for n. If, for example, we bump into 1,000, we land much closer to the unit circle. So could this result be correct? Is it consistent with all the nice exponential and logarithm properties that we've seen thus far? And can it help us figure out the relationship between b and theta in the unit circle equation we derived earlier for 2 to the power of bi? Let's go ahead and rewrite this equation in terms of the base e to better line up with Briggs' equation. Since b is just an arbitrary constant, we can introduce a new variable b is equal to c divided by 0.693, just as we did with Briggs' equation. Substituting, we can rewrite our equation as e to the ci is equal to cosine theta plus I sine theta. And our job now is to find the connection between c and theta. When we plugged I into Briggs' equation, effectively using a c value of 1, and used an n value of 1,000, our result was a complex number with a magnitude of 1.0005 and an angle of 57.296 degrees. This angle should be equivalent to the theta value in our cosine plus I sine theta equation when c equals 1. So when c equals 1, theta equals about 57.296 degrees. Let's plug in more values of c into Briggs' equation and see how theta changes. Plugging in the values 0 through 5 for c, a pattern emerges for theta, with theta increasing by a constant value of about 57.296 degrees for each increase of c by 1. So this result is telling us that if we raise e to the imaginary powers of I, 2i, 3i, and so on, our answer moves around the unit circle in equal steps of about 57.296 degrees. Now, if we make a small change and measure theta in radians instead of degrees, we see something truly remarkable. Each increase of c by 1 moves theta by 180 divided by pi, or exactly 1 radian. So if we measure theta in radians instead of in degrees, the value we've been calling c is exactly equal to theta. Finally, we've arrived at Euler's incredible formula. E to the power of I theta equals cosine of theta plus I sine theta. Now, before we celebrate too much, we never really check that Briggs' formula makes sense when our inputs are imaginary. After all, Briggs developed his formula by zooming in on a very real exponential curve that has nothing to do with imaginary numbers. When we plugged in I into Briggs' formula using n equals 6, we saw that visually this looks like 6 thin triangles stacked together to form an overall angle. Each triangle has an angle of 9.46 degrees. And when we multiply this number by itself 6 times, these angles are added together to produce a final angle of about 57 degrees or 1 radian. As we increase n, we get more and thinner triangles and a more accurate estimate of e to the power of I. Considering our first thin triangle for a moment, if n is 100, for example, then the base of our triangle is equal to 1, the real part of 1 plus I over 100, and the height of our triangle is equal to the imaginary part, so 1 over 100. Now, where it gets interesting is if we consider the connection between the small angle of this thin triangle, let's call it delta, and the height of our triangle. From trigonometry, we know that the tangent of delta equals the height of our triangle divided by its base, so 1 over 100 divided by 1. Now, just like the exponential function, it turns out that if we zoom way into a tangent function, it also looks just like a straight line. And the slope of the tangent function in the neighborhood close to 0 turns out to just equal 1. So for small values of delta, the tangent of delta just equals delta. What this means for our thin triangle is that as n approaches infinity, the height of our little triangle exactly equals our angle delta when delta is expressed in radians. Now, fitting all the pieces together here, taking some imaginary exponent ci, Briggs' formula tells us to divide c by n. This effectively gives us a thin triangle with a height of c over n. And if n is big enough, the small angle of this triangle is equal to c over n radians. Now, Briggs' formula tells us to multiply this triangle by itself n times, which using the polar form of complex numbers means we add our angle delta up n times, which gives a final angle of c over n times n, or just c. This is why c is equal to our final angle theta expressed in radians. Just as Briggs' formula linearized the exponential curve for real exponents, it's remarkably able to work in a similar way for imaginary exponents. In the imaginary case, this happens in the 2D space of the complex plane, and it works out because we can linearize the tangent function for very small triangles. And because multiplying all these little complex numbers together results in rotation on the complex plane, we end up with rotation instead of growth. Now that we have Euler's formula, we can finally see how he saved calculus. We left off with Euler arguing that both Leibniz and Bernoulli were wrong, and that the log of -1 has more than one correct answer. If we take the natural log of both sides of Euler's formula, we're left with I times theta is equal to the natural log of cosine theta plus I sine theta. Euler was interested in the case where the argument of the logarithm is -1. This will happen whenever the cosine term equals -1 and the sine term is 0. On the complex plane at the point -1, 0 on our unit circle. A theta value of pi radians will work here, but so will -pi, 3pi, -3pi, and so on. So the logarithm of -1 is equal to all odd multiples of pi I. This is precisely what Euler means when he says that logs have an infinite number of solutions. Euler's paradox about the logarithm of -1 squared now has a straightforward solution. If we drop the 2 down, this means multiplying all the solutions of log of -1 by 2. So -6pi, -2pi, 2pi, and so on. Now the contradiction came up when we squared the -1 first, instead of dropping it down. This gives us the log of 1. Using Euler's formula, the log of 1 will happen when the cosine term is equal to 1, and the sine term is equal to 0. So at angles of 0, 2pi, -2pi, and so on. As Euler points out in his paper, the solutions to 2 times the log of -1 are visibly contained in the solutions to the log of 1. This fact, along with a number of other impressive results, convinced Euler that defining logarithms and exponentials in this way would save the foundations of calculus. Euler's approach was highly controversial at the time, but would eventually gain acceptance. Personally, I don't think it's surprising that Euler's formula and his approach to logarithms was so controversial. If we just look at Euler's formula, it's pretty absurd. To the right of the equal sign, we have cosine and sine waves from trigonometry. To the left, we have e raised to a power, which typically means exponential growth. The wild card here is, of course, the imaginary unit I, which, as we've seen, is almost as if by magic, turning exponential growth into periodic wave-like motions. We began our discussion with the idea that many of the equations and graphs we spend our time with are just shadows of a more elegant, powerful, and higher dimensional mathematics. The deep connection between exponentials on one hand and sine and cosine on the other is perhaps the most stunning example of this in mathematics. If we take a polynomial function like x squared plus 1, expand its inputs and outputs to be complex numbers, and visualize one of these imaginary parts of the function as the height of a surface above the real plane, we get these cool paraboloid shapes. Incredible, but perhaps not a surprising extension of parabolas to complex numbers. But when we take the familiar exponential growth function of real numbers and expand its input and outputs to be complex numbers using Euler's formula, the surface that emerges incredibly is shaped exactly like sine and cosine waves. The projection of the surface in one direction is our familiar exponential curve, and in the other direction are cosine and sine waves. And this structure is not some invention. It literally falls out of our familiar rules of algebra, carefully applied to imaginary numbers. All of these pieces of mathematics somehow fit together perfectly into a form we could have never imagined, making Euler's formula the most beautiful equation in mathematics. If you want to get deeper into imaginary numbers, I really think you'll like my book. Way back in 2016, I made a massive 13-part YouTube series on imaginary numbers. It's such an incredible topic. I released an early version of this book back then, and I'm now in the process of revising, correcting, and significantly expanding it. My goal is to create the best book out there on imaginary numbers. High-quality hardcover printed books will start shipping later this year. You can pre-order a copy today at the link in the description below, and your order includes a free PDF copy of the 2016 version that you can download today. I also made a poster version of the table from this video that walks through the incredible path to Euler's formula. This is the first dark mode poster I've done, and I'm super happy with the look and feel. This poster is a great visual explanation of the path we took here to get to Euler's formula, and I also just think it looks cool. You'll find all of this and more in the Welch Lab store.
Incredible. I would have never have imagined that it's so complicated. How could we live without YouTube? I have to go get more gum before I kill myself. Ugh.
actually get to a cinema that's willing to screen this. And the reason it's in so few cinemas is that there have been leftist activists that have threatened these places of business. Do not air this movie. Like, it's absolutely insane. It's ridiculous, right? So, in order to actually make money, in order to actually make something profitable, you do not need CGI. You do not need remakes. You do not need any of the stuff that Hollywood is coming up with. You don't.
Mm-hmm. Mm-hmm.
These are not people RT groomed as assets, they're people RT recognized as assets.
That is a really important part because a lot of people were like, well, I mean, they could have done the same thing to leftists. And I was like, no, they couldn't. Did you see the listings that you have to talk about? How people of color have privilege in society, the degeneracy of perverts, how white people are being replaced for voter demographics, upcoming civil war. All these are all, yes, talking points in which if you presented it to a Tim Pool or Dave Rubin or Lawrence Southern, that's the kind of things you already talk about. Last YouTube for his channel, YouTube says that he deleted it himself. They shut down a different channel, which he didn't post to. Last week, the Department of Justice indicted 2 Russians for secretly funneling money to American right-wing video personalities. Shortly after, YouTube cracked down on the entity behind the scheme, Sam Media deleting this channel and the 4 others run by Lauren Chen. The next day, Taylor Hansen, reporter and former employee of Tenet, announced in a post on X that he'd been permanently banned from YouTube. And I just got permanently banned from YouTube. Hansen wrote on September 6th, and a post that garnered 2.4 million views. The text in the notice that the channel had been removed, not that it had been permanently banned. This is 100% targeted, with no explanation has been given despite the DOJ indictment explicitly stating that the show host reporters were victims if the allegations turned out to be true. Hansen added in a follow-up post. In the indictment, the DOJ noted the personalities sent paid.
Oh, this is Dr. Grande. Today's question is, can I analyze the case of Lucy Letby? Just a reminder, I'm not diagnosing by this video, only speculating about what could be happening in a situation like this. If you enjoyed this video, please like it, subscribe to my channel, and consider supporting me on Patreon. I'll put the link to Patreon in the description for this video. First, I'll look at the background of this case, move to the timeline of the crime, then offer my analysis. Lucy Letby was born on January 4, 1990 in Hereford, England. She was an only child. Lucy attended the University of Chester to study nursing and worked as a student nurse. She graduated in 2011 and started working at the Countess of Chester Hospital. Lucy was assigned to the neonatal unit. Now moving to the timeline. In 2015 and 2016, the hospital where Lucy worked was plagued by an unusually high mortality rate in the neonatal unit. Consultants were brought in to conduct medical reviews and found that the death rate was dramatically elevated. The unit had recorded 15 fatalities, more than double its annual average. The consultants noticed that Lucy Letby was on the unit when several of the unexplained deaths occurred, but they didn't have any direct evidence that she had caused the deaths. Unable to figure out what was going on, the hospital made a decision in July of 2016 to no longer accept premature infants born before 32 weeks. Another review was carried out in November of 2016, but this one also failed to identify the cause of the high mortality. Lucy was advised that the consultants suspected her involvement in the deaths. She filed a grievance in response. In January 2017, 2 reviews concluded that Lucy had not engaged in any wrongdoing. The consultants were forced to apologize to Lucy. She was allowed to return to work on the unit immediately, but she never did. In March of 2017, the consultants advised the hospital that it was time to notify the police. After conducting an investigation, the police came to believe that Lucy was responsible for several murders and attempted murders. After being arrested and released twice, once in 2018 and once in 2019, Lucy was arrested for a third and final time on November 11, 2020. She was charged with 7 counts of murder and 15 counts of attempted murder. Lucy's trial started on October 10, 2022. The Crown argued that Lucy killed and attempted to kill several infants using a variety of methods, including injecting air, poisoning with insulin, overfeeding, and attacking them with medical instruments. Lucy's defense argued that many factors contributed to the deaths. They claimed that several physicians engaged in a conspiracy against Lucy. There was a lot of information for the jury to consider. For example, 300 witnesses testified. There were 32,000 pages of exhibits, and the jury was provided a 25-page glossary of medical terms. The jury started deliberations on July 10, 2023, and started returning verdicts on August 8, 2023. When the final verdict was reached on August 18, all the verdicts were made public. Lucy was found guilty on 7 counts of murder. Her victims were 5 premature boys and 2 newborn girls. She was also found guilty of 7 counts of attempted murder, which involved 6 victims. Lucy was found not guilty on 2 counts of attempted murder. The jury could not reach a verdict on 6 counts of attempted murder, which involved 5 alleged victims. Lucy Letby is facing up to life in prison without the possibility of parole. Now moving to my analysis. Here are my thoughts on a few items that stood out to me in this case. Item number 1. There's not much question that Lucy is guilty. The excess mortality was significantly elevated when Lucy was on the neonatal unit. When Lucy was removed from the unit in July 2016, the safety record improved dramatically. Since that time, the unit has cared for over 2,500 babies and recorded only 1 fatality. They were caring for infants who were at risk from the time that Lucy was there, but that is still a significant difference. The police constructed a chart showing how Lucy was on duty during every incident. She is the only factor that connected to all the murders and to all the attempted murders. In addition, Lucy wrote a note which could be considered a confession. This brings me to item number 2. After Lucy was arrested for the first time in July 2018, the police searched her residence and found a handwritten note. Here is a summary of that note. Lucy wrote, quote, "There are no words. I'm an awful person. I pay every day for that," unquote. She talked about how she could not breathe or focus. She had overwhelming fear and panic, and she was alone and scared. Lucy complained that she would never get married or have children. She would never know what it was like to have a family. Lucy wrote, quote, "I don't deserve to live. I did this. Why me? I killed them on purpose because I'm not good enough for them, and I am a horrible, evil person," unquote. She argued that the world was better off without her. At the end of the note, in all capital letters, Lucy wrote, quote, "I am evil. I did this, unquote. This note appears to have been written when Lucy was experiencing intense emotions, including guilt and shame. She was struggling with her status as a killer. Lucy recognized that her behavior was wrong and realized that she had caused great harm. I think this note demonstrates how Lucy did not have much insight. She knew that she was driven to kill, but she did not understand why. She adopted the simple explanation of being evil, horrible, and awful. I find it curious that Lucy used the term, why me? Almost like her behavior was outside of her control. She was selected by a mysterious entity to be an evil killer through no fault of her own. She thought of herself not only as a perpetrator, but as a victim. Lucy failed to see her behavior as indicating the presence of mental health symptoms, although she did mention not being good enough. Perhaps Lucy had low self-esteem. Item number 3. On a few occasions, Lucy attempted to kill the same victims repeatedly. Sometimes she achieved her goal, and other times the infants were saved by being moved to a different hospital. There may have been some type of personal component that contributed to Lucy's behavior. She did not view the infants equally. She became fixated on some of them for whatever reason. Lucy really wanted certain victims to be dead and was willing to take tremendous risks to achieve that goal. This behavior demonstrates a tendency to become obsessed. Item number 4. Lucy engaged with the family members of some of her murder victims, telling them how sorry she was for their loss. After murdering one victim, she sent the family a sympathy card. Lucy used her cell phone to capture a photograph of that card before sending it. During one incident, Lucy had to be told more than once not to enter the room containing grieving parents. These parents were grieving the loss of a child who Lucy murdered. There was something about the grieving process that was attractive to Lucy. She appeared to be drawn to strong emotional experiences in general. To Lucy, it didn't matter if the emotions were positive or negative, as long as they were intense. By murdering children under her care, Lucy created intense negative emotional experiences that attracted the attention of everyone, grieving family members, hospital staff, and eventually investigators. Initially, many people felt badly for Lucy and encouraged her by telling her that she was a good nurse. Lucy was being treated like a victim too, which is exactly what she wanted. There's the sense that Lucy thrived on frustration, despair, anguish, confusion, and grief. The suffering of others was exciting and fulfilling to her. She just could not get enough of that feeling. No amount of homicidal behavior could satisfy her. Item number 5. What do I think happened in the case of Lucy Letby? This is just a theory, my opinion. One possibility in this case is that Lucy was suffering from something like factitious disorder imposed on another. This is also called Munchausen syndrome by proxy. This is a disorder.
Oh, you didn't hear what I said. I said Munchausen by proxy, but you didn't hear me.
Where a caregiver intentionally induces, falsifies, or exaggerates manifestations of physical or mental health symptoms in a person who is under their care. Here are some of the typical characteristics of those who have the disorder. They have extensive knowledge of medical terminology. They are sadistic and enjoy seeing victims suffer. Their undesired behavior is persistent. It's rare that somebody with the disorder commits just one offense and then terminates their criminal career. They often present as overly attentive and attached to the victim, and they want to be viewed as a victim themselves. They love getting attention and sympathy for others. The motivation for factitious disorder imposed on another is often conceptualized as unconscious. The individual doesn't have insight, but they do understand the wrongfulness of their behavior. They conceal their crimes because they do not want to face consequences. They know that they would be arrested and sent to prison. Another notorious killer nurse in Britain, Beverly Allitt, was diagnosed with factitious disorder imposed on another. I'll talk about her case in a moment. One could argue that Lucy's behavior aligns with factitious disorder symptoms, but of course there's no way to know for certain if she actually has the disorder. There may be some other explanation which has nothing to do with mental health. Either way, I think it is reasonable to believe that Lucy killed because of the way it made her feel. She desired an emotional experience that could only come from killing the most vulnerable members of society from a position of tremendous trust. Lucy was self-centered, manipulative, sadistic, had a profound lack of empathy, and had little insight. She was willing to meet her needs at any cost. Item number 6. As I mentioned, Beverly Allitt was another notorious serial killer in Britain. Just like Lucy, Beverly was a nurse who killed children under her care. Beverly was convicted in 1993 on 4 charges of murder, 3 counts of attempted murder, and 6 counts of causing grievous bodily harm. She was sentenced to 13 terms of life in prison. She is still incarcerated, but was technically eligible for parole starting in 2021. Let's take a look at Beverly's history compared to Lucy's history. Starting with the similarities. Both women had an interest in working as a nurse in a hospital unit which cared for children. Both were described as
This is a double introduction, a series in a series. The foundational series is Dangerous Minds, where we explore dangerous minds from the perspective of a dangerous mind. That's me, in the hopes that we all learn to stop being so open-minded. Our brains are starting to fall out. The inner series is about a specific type of danger, which dangerous minds use to trap innocent students. I present the definition and description of the tar pit, but I will let my friend Diego present what it means to be a dangerous mind, which also introduces us how to avoid tar pits in the first place. The purpose of this series: trust no one, not even me. Your mind is capable, trust me, but don't, but do, whatever. All that being said, take this intro as gospel.
One of the worst things you can do is while you're learning new ideas is allowing your mind to take in bad ideas during the process, to muddy the water. If you don't treat the truth as dogma while you're learning, and you're never going to integrate it as a good habit. So in my opinion, you should avoid arguments. You should avoid people in your life that may provide value in some way, but psychologically, subconsciously, they're going to still kind of keep on filling your mind with questions. The way, as Puya said it, no, you push them aside while you're learning, and then you have to integrate the truths and the dogma over time. So one of those things, if you're learning to clean your mind of this junk, you should avoid really other people, period. At the start, I treat people like a doctor or a philosopher. As a philosopher king, I can't be skeptical.
Accessible University. Oh, let me say something about Accessible University. Go off. You're a detriment to people trying to better themselves. You're a disgrace. Gosh darn it, that old
Diego, quick to judge, made instant assumptions.
I think listening to him is harmful. You should stop. Really.
Existence University says, I don't believe any of that.
Oh, you don't?
Okay.
That's fine.
Oh, well.
I want your messages in my chat. All right, we're getting to Destiny here. Here we go. And he's done the 30 years of research to figure this out. He didn't just rationalize this out of his hole. So no, you are a danger to anyone trying to learn objectivism. You are a danger.
Tar pits. An introduction to nothing. What is a tar pit? In philosophy and science, there is a lot of information to parse through, and the task is made difficult by the fact that not only is there about 20,000 years of history in the topic, but also that we only started to write that information down 5,000 years ago on materials that didn't last to the present day. And further, that this history has been interwoven by billions of people, getting only a fraction of a percentage of the total, in what can be considered the longest game of Chinese whispers ever played. And worst of all, it is not considered to be anything like Chinese whispers, and that we are supposed to just take whatever a person with the title of philosopher or scientist says as true. The amount of atheists, for example, that cry, "But Kant said," disregarding the fact that everything Kant said was in order to invent a god and denounce reason. But Hume said we cannot have reason, disregarding the fact Hume said that, so he could
We do begin, though, with breaking news. A rapid escalation in fighting between Israel and Hezbollah, a militant group based in Lebanon, to Israel's north. Israel's military says 2 soldiers were killed by Hezbollah strikes in northern Israel, and the Israeli military started striking Hezbollah targets in Lebanon today, saying it has plans to do more in what it calls the northern arena. The Israeli strikes came just minutes before the leader of Hezbollah spoke for the first time since those deadly device explosions in Lebanon. He said that those explosions crossed a red line and could be called a declaration of war. The number of people killed by the exploding pagers and walkie-talkies continues to rise. Some video there, at least 37 people have died. Thousands more have been injured. So far, there are no reports of any new device explosions today. Joining me now, NBC News international correspondent Josh Letterman. Josh, there have been a lot of moving parts today, a lot to track. What else is the Israeli military saying about its strikes against Hezbollah in Lebanon today?
Well, Israel is confirming that its forces have been bombarding southern Lebanon, not only with airstrikes, Kate, but also with artillery. But importantly, a senior official told NBC News that Israeli troops are not crossing the border on the ground. In other words, this is not the start of a potential ground incursion into Lebanon that many have been fearing for quite some time. But in the last hour or so, we also heard from the Israeli defense minister in a briefing about what's happening on Israel's northern border, where he once again called this a new phase of the war. He said that in this phase, there are opportunities for Israel, but also significant risks, and that the sequence of Israel's military actions will continue. So he seems to at least be suggesting that this could not be over. And in fact, if you listen to what Hassan Nasrallah, the leader of Hezbollah, said today, he also indicated that they think that the Israeli actions may not be finished. And so you take all of this together, and there's certainly a significant concern about the potential for further escalation in the coming hours and days, Kate.
Josh, thank you. Let me bring in NBC News national security and global affairs reporter Dan DeLuce. Dan, we mentioned before there have not been any new explosions of devices in Lebanon today that we know of. I know you just spoke with a former senior Israeli security official about those blasts. What did he tell you?
He's saying that those were basically targets of opportunity, that this was a use it or lose it moment, as they put it. In other words, this was not a part of a larger strategic operation that was supposed to precede some kind of major ground and air assault on Lebanon, that there was a temporary window where they could use this capability they had, by tampering with these pagers, and they used it. So that is an interesting insight. That's also really the working assumption of Western governments, the U.S. government as well. And then just to echo what Josh is hearing here in Washington, the Biden administration does not at this moment believe that Israel is using those pager attacks and exploding walkie-talkies to launch some wider major offensive on Lebanon. That obviously it's a fluid situation, and we don't know exactly how Hezbollah is going to respond after really a humiliating setback with these exploding communication systems that's just caught them completely by surprise.
Yeah. Dan, thank you. Josh, let me go back to you. We've been hearing from doctors treating people injured by those device explosions, and one of the doctors described wounds that she had never seen before. What else are we hearing?
Well, Kate, NBC spoke with the chief medical officer of the American University in Beirut Hospital, a major medical center there, who said they've never seen this kind of pace of injuries. They've seen about 150 people coming in. They say that there are 12 operating rooms at that hospital. All 12 have been operating around the clock, essentially no separation where they don't have somebody undergoing surgery on their hands, on their eyes, on their face. They say that right now they have the supplies they need, but it is a very concerning and fluid situation.
Thanks for watching. Stay updated about breaking news and top stories on the NBC News app or follow us on social media.
A longtime CIA officer has been sentenced to 30 years in prison for sexually assaulting more than 24 women. Federal prosecutors say Brian Jeffrey Raymond drugged, photographed, and assaulted the women at his postings around the world, dating back to 2006. 48-year-old was found to have had more than 500 images of his victims. Yesterday, Raymond said, quote, "There are no words to describe how sorry he is." Authorities praised the victims who came forward, about a dozen of whom were there in the courtroom. One of those women said afterwards, quote, "I hope he is haunted by the consequences of his actions for the rest of his life."
is from electromagnetism to optics. And in this particular video, I'm going to try and motivate the whole topic. Now, why do I think this is important? Most university students will begin a course in optics somewhere in the first or second year in university. It'll usually start with a course in geometric optics and perhaps also taking elements of wave optics. Now, once we begin doing wave optics, things get, they get reasonably complex. However, the foundations for optics will not have been covered because people do not do courses in electromagnetism until at least their second year in university. Why is this observation important? Well, because electromagnetism is the foundation of optics. So without electromagnetism, we do not have optics, and the converse does not hold true. Now, in order to do a beginner's course in optics, you do not need to be very proficient in classical electromagnetism. What you do need to do is to look at the results from electromagnetism, take the results, take the predictions, and move forward. So in one sense, you can kind of forget that electromagnetism is the foundation of optics. And this should make sense to you because think about your computer. In order to I don't know, let's say write a piece of code or write a program on your computer. In theory, you could write that piece of code by just looking at the atoms and the molecules in the computer itself. That's very difficult. It works, and we came up with computer programs. So we could technically, of course, write a computer program by just looking at the atoms, but we don't do that, which now is just so difficult. But of course, we don't do that because it would be very cumbersome. We're going to be talking about wave optics, so this is very important. I'm going to discuss where where you get something looking like this. Why do we use x plus or minus vt? I'll discuss that in video number 2. I'm going to discuss the wave equation, sinusoids, complex exponentials. Why do we use complex exponentials instead of the sinusoids themselves? And I'm going to discuss the wave function, which is a solution to the wave equation. And all of this, of course, it falls out from Maxwell's equations. So I'm going to give you a brief description of Maxwell's equations and why they're important. Basically, bottom line up front, Maxwell's equations govern all of optics. And without them, you have nothing, or with them, you have everything. So just so you've seen once, I'm going to write them over here. Okay, so there are 4 equations. So the first one we have that the divergence of the electric field is equal to the charge density over epsilon 0, the permittivity of free space. We have that the curl of the electric field is equal to minus the time rate of change of the magnetic field. We have that the divergence of the magnetic field is equal to 0, and we have that the curl of the magnetic field is equal to permeability of free space, the volume current density, plus mu 0 epsilon 0, and then we have the time rate of change of the electric field. So these are the 4 equations which we collectively know as Maxwell's equations. So this one here is Gauss's law for the electric field. This is Faraday's law for electromagnetic induction. This, I suppose you could call this Gauss's law for magnetic fields, but people usually just call it nameless, or say that it is nameless, excuse me. And this one here is Ampere's law. So we're going to discuss all of this quite briefly, just to gloss over it, I suppose, but give you reasonable confidence moving into your course in optics. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also give me some comments. Thank you. Okay, in this video, I'm going to continue on with my tutorials, moving from electromagnetism to optics. This is video number 2, and I'm going to discuss waves. Specifically, I'm going to show you why we use F is x plus or minus v times t. So the previous video, which is relevant to this, is number 1, where I try to motivate the topic of moving from electromagnetism to optics. And before I begin, I'd just like to point out that I'm using a new recording setup. I'm actually clearly recording on e-paper rather than using a camera. So you're going to have to, I suppose, excuse my handwriting. It's not as good as it would be on regular paper. So what are waves? We need to, I suppose, define what a wave is. So a wave is a disturbance, and it's usually a disturbance of a medium. And intrinsically, we have an understanding of what a disturbance of a medium is like. For example, we know what waves in a string are like, waves in the water or waves in the air. But we're going to be dealing with electromagnetic waves. And the reason these are important or interesting or special is because they do not require a medium to propagate. If you'd like to know more about that, just Google perhaps the luminiferous ether. That was a big problem or a big question in physics perhaps 100 years ago. So how do we generate a wave? Although we're going to be discussing electromagnetic waves, it's easy, I suppose, or helps us to think about them as mechanical waves, for example, a wave on a string. So on the left, the black line, bottom left, the black line perhaps represents a string. And what I've done is I've picked up the string and I've dropped it down, creating a wave which is propagating in this case to the right. And it's propagating to the right with a speed v. So that's our wave. So it looks something like this, if you were to zoom in on it. And this particular profile is called a Gaussian. And the functional form for Gaussian is e to the minus ax squared. So a is just a constant giving you the height, and then you have x squared. Okay, so just note that this is called a Gaussian function or Gaussian form. You'll see that it's all over physics. You can't move anywhere in physics without looking at Gaussian waveforms. So the next thing we need to discuss is what is the placeholder given to a wave. So for writing the wave down, well, we use the Greek letter psi. So if you look at the bottom left, we have the Greek letter psi. And so in order to create our wave, we need to have the dependence on position, and we need to have dependence and we need to have dependence on time. So we have 3 spatial dimensions. We have x, we have y, and we have z, and of course we have time. But we can have, depending on how many spatial dimensions we talk about, a 1-dimensional wave, 2-dimensional wave, or a 3-dimensional wave. All right. So in this particular case, what I've drawn is the wave psi, a function of only x and t. So it is a 1-dimensional wave. But if you were to write this, it would be, let's say instead of using psi, let's say y is a function of x and t. So that leads us to say psi is the wave function. So that's why we call psi the wave function, because it gives the mathematical form of the wave itself. All right. So what we're looking at here is a 1-dimensional wave function. Right. So what can we do with this? Well, the shape of the disturbance of the wave at any instant can be found by holding time constant at that time, or that case. So let's take a Gaussian. So let's e to the minus a, and just accept what I'm about to write for a moment, x minus vt. Let's say that this is our wave function. It's a 1-dimensional wave function, and this actually gives us the shape of a Gaussian wave function moving to the right, or Gaussian wave moving to the right. Now, if I want to find out what the wave looks like, let's say I want to find out a time t is equal to 2. I want to see what the shape of the wave looks like. What I would need to do is get rid of t and put in 2. Or if I want to find out what the shape of the wave is like at the start, at time t is equal to 0, then of course you plug t is equal to 0 in here. You plug t is equal to 0 in here. All right, so that's how we find out what the shape of the wave is. And what we get, if we plugged in, this should be that's v, let's check there now. That's v times 0. And if you plug that in, what you actually find, you'd get this here. Okay, and let's say this here is t is equal to 2. Then what we've gotten earlier on is this particular shape here. So that is our wave function. Now, we will start just deriving x. F is a function of x plus minus v times t. So when the wave moves, you can either move with the wave or look at it from a distance. So what we're going to do is consider what the wave looks like for 2 different people, or 2 different observers. So let's say I have let's say I have my Cartesian coordinate system here. Okay, I'm going to call this particular Cartesian coordinate system, say there's y, that's y and x. But you'll see more when right, there's x, and we have generate a wave. So I'm just going to draw my observer here. This is my observer with his hat, and let's generate the wave. So here's my wave, like this, and the wave is propagating to the right with a speed v, or the velocity v, I suppose, has a direction. And let's say there's another person, another observer, and this observer is moving along with the wave itself, and he's moving along with the wave itself. So at some point later, so we want to analyze what the wave looks like for the person with the wave and the person at the origin, or in the S frame of reference. So the person moving with the wave is going to be in S prime frame of reference. So we're going to have x prime, y prime, and s prime. And of course, the wave then, the wave is going to look something like this. Well, it's going to look the exact same because we're not going to change we're not going to change the shape of the wave. So that means we need to draw our observer as well. So bear with me, and I draw this. This person is traveling along with the wave. Now what we want to do is see what does the wave look like for the person in blue and the person in red or pink. So what does it look like for the person standing at the origin watching the wave propagate away and the person propagating with the wave, moving with the wave. Now there's a very important thing to note here, and that's the person moving with the wave doesn't see its profile change. As far as it's concerned, the wave is stationary. Okay, so there's no dependence on, it looks the same. It's not changing. It's not moving anywhere as far as he's concerned. So let's look at some of our distances. First of all, note that the distance from the S frame of reference, sorry, this should be S, I'm going to get rid of it. This is the S frame of reference. So the distance from the S frame of reference to the S prime frame of reference, or the distance from the origin to where the wave is now, is going to be the velocity of the wave multiplied by time. Now, the distance then from the observer in the S frame of reference to the center of the wave, where it is now, is going to be this distance here. And let's call that distance x, because the reason it's x is because we're talking about the S frame of reference with x. However, for the observer who is with the wave, he only sees this distance. So he sees x prime. And if you put the lot together, then we find that x prime is equal to x minus vt. It's very straightforward. Now, I'm sure you can accept that if the wave is moving to the right, we would actually get plus sign here. So we can say that in general, x prime is x minus v times t, or plus minus v times t, depending on which way it's moving. So what we can say is this, that if it's x minus vt, it's going to the right. And if it's x plus vt, it's moving to the left. All right? So that's important. Now we're after working out what the dependence on the wave is when it's moving. So this is, of course, from the observer at the origin, the stationary observer at the origin, the person who is not moving with the wave. So the thing about, we had a moment ago, we said that the wave function, psi, is a function of x and t. But we can see here that this is for the observer at the origin, or the stationary observer at the origin. But it can also be written as psi function of x prime. This is for the person moving with the wave. Now, why is there no time dependence? Well, because the shape of the wave, or where it's going, is time independent. Because as far as he's concerned, the wave isn't moving, it's just standing there. But for this observer, the wave is moving, so there's a time dependence. So you can have psi as a function of x and t, or simply a function of x prime. So we of course know that we can rewrite this because we know what x prime is. So we get x plus or minus v times t, like that. And I want to rewrite this because it's a function of v times t, so I'm actually going to write f like this. Okay, so some positive feedback. Thank you. Okay, in this video, I'd like to talk about electromagnetic waves. This is aimed at somebody who's doing a course in optics in college. Okay, in this video, I'm going to continue on with my tutorials of the one-dimensional wave equation, x in the function. So we saw earlier on, as I said, that we have e to the minus ax, it was e to the minus ax squared, which becomes e to the minus ax plus or minus v times t to be squared. And that's where we get x plus or minus v times t. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also click on or give me some positive feedback. Thank you. Okay, in this video, I'd like to talk about electromagnetic waves. This is aimed at somebody who's doing a course in optics in college, and I'm going to talk about how we derive a wave equation and so on. It's going to be pretty basic. Okay, this is kind of the fundamentals. But I would like for you to watch my video on wave-particle duality. And I know that video is quite long, but it'll give you a good insight into how we model light. Or you might even watch my video on scientific models. Okay. Now, in this particular video, I'm only going to be talking about the wave model of light. All right. So the first thing I'd like to say is, if you look at those videos, you'll understand that we describe light as, we can describe light as moving as a wave, just like waves on a string or the waves in the sea. However, these ones don't need a medium, or they don't need something to move through. They can just move through empty space. And if you always want to describe things mathematically from reason physics. So can we think of a function which constantly repeats itself over and over and over again? And the answer is we can. We know that sines and cosines do that. So you should think it reasonable that when describing electromagnetic waves or light waves, that we use sines and cosines because they constantly repeat themselves, just like the light waves do. And we use the Greek letter psi to illustrate, or to represent a wave. And because a wave can be somewhere in space, we should know that we should think it reasonable that the wave depends on its position and it depends on its time. Of course, we can generalize this and talk about it in 3 dimensions, but that's more difficult. So I'm only going to talk about the one spatial dimensional case. So t, time for temporal dimension, and x for spatial dimension. All right. So that's all I've got to say about that particular thing. So how about we work out how do we find out its position? All right. Now the other thing as well is that I won't mention that now. All right. So I'm going to suggest to you that a wave will look something like this. Psi is equal to a times, that's just the constant that gives kind of the amplitude of your wave, times the sine of k x plus or minus vt. And you might say, oh, where did that come out of? And I'll tell you. Well, a is just, remember, sine is between 0 and 1. So if you multiply it by a number, you can get any number you want. So that's how you get the amplitude of your wave. Now, when people were analyzing electromagnetic waves or sound waves, they found that a particular number kept popping up, 2 pi over lambda. And they called that k, which we call the wave number. And that was great. It was probably initially used first because they didn't want to write 2 pi over lambda. But they found since that it has a physical meaning, and the physical meaning is it gives you the direction of movement or direction of propagation of your wave. So we know, for example, that electric and magnetic waves are perpendicular, something you should, I've spoken about in other videos, but anyway, we know they're perpendicular. So the wave number k is perpendicular to both of those and gives you the direction of propagation of your wave. Okay, and it is a vector. But in one dimension, we just call it 2 pi over lambda, which is just one particular dimension, a number. So like I said, your wave number is there, and you don't need to worry about why it's there. Just know that this thing was seen to need to be there, and it actually has a physical meaning because it gives its position, or it gives you, the direction of movement. And I told you that our wave equation is a function of position and a function of time. Well then, say that's position x, then psi is equal to a times the sine of kx, we'll say. So let's go ahead and work that out. So say if I say the wave moves, so the wave is after moving, and say there's another person there, okay? Say there's another particular individual there, and he has his own frame of reference, so he calls it S prime. So how far is so we know that is equal to the distance, is Vt. Well, how far is it now? It might be another X prime. 1 second, X prime. This is X. Sorry, I take that back. That's a silly thing to write. So we'll say that in the frame of reference of the new wave, he considers his position to be X, but in the old frame, he considers himself to be at X prime. Well, he considers that to be a distance X prime. So how do we work out the distance here in terms of the person that's there? So we'll say that X prime is equal to, or the X, excuse me, is equal to X prime minus Vt. All right, I think I got confused there a small bit myself. So just to say it once more, that your wave is here initially, and this person considers the wave to be there. That's fine. Then the wave moves away, and now its position can be thought of relative to this person or this person. And the distances are there. So in this person, you might think the distance that the wave is from him is x, whereas this person thinks the wave is x prime away. And the wave, or the distance between the two frames, is the distance of the speed of the wave times the time. And we'll say you get x plus v came from. Just if you can understand, you can rewrite that equation if you like. There's one more thing I don't feel, or you. All right. Or we'll say to there. Now on the piece of paper, because it's moved, I'll have a.
Okay, in this video, I'm going to continue on with my tutorials, moving us from electromagnetism to optics. This is video number 3, and I'm going to discuss the wave equation. The previous video to this, which is relevant, is number 2, where I discussed waves, and I showed you why we use f as a function of x plus or minus v times t. So once again, this is a new way for me to record via e-paper, so you're going to have to excuse my writing. I'd like it to be better, but it's not yet there. So in the previous video, what we showed is as follows. Just a very quick recap. We said that when we're talking about waves, we give placeholder psi for the waves. And we'll say if they're a function, if it's a one-dimensional wave equation, it'll be a function of position and time. So we call this the wave function because it describes exactly what the wave looks like. And for example, we might have e to the minus a outside of x plus or minus vt squared, and that gives us a Gaussian wave function moving to the right. It gives us moving to the right if it's minus v times t, and moving to the left if it's plus v times t. So that's our wave function. And the important point to remember here is that when we're deriving this, we spoke about the person at the origin watching the wave move, and we spoke about the person who is moving with the wave in the prime frame of reference, and he might be here. And what we did here, this x plus or minus v times t brings us from the s prime frame of reference back to the s frame of reference. So now what we seek to do is to use the information derived in the previous video to develop a general form of the one-dimensional differential wave equation. Now, why do we want to have a differential wave equation? Why are there going to be derivatives involved in this? Well, because we're talking about rates of change. We're talking about a dynamic system. It's going to change, and as a result, we need to discuss derivatives because derivatives are what discuss rates of change. It's quite intuitive, I suppose, in that respect. So to that end, what we need to do is start taking partial derivatives. Now, I'm not really going to go into the mathematics behind it. Just accept that in order to derive the wave equation, we need to start taking partials. So what we're going to do is, first of all, we're going to take a new color to start. So we're going to take the partial derivative.
I don't know where he's taking this. This is from 11 years ago. I don't know what's going on here.
If you track the motion of individual stars in the ultra-dense star cluster at the very center of our Milky Way galaxy, you'll see that they swing in sharp orbits around some vast but invisible mass. That's the Sagittarius A star supermassive black hole. Now, these are perilous orbits, and sometimes a star wanders just a little too close to the lurking monster, leading to its utter destruction in a spectacular phenomenon known as a tidal disruption event. Now, we've never seen a TDE in the Milky Way, but we've seen them in other galaxies, and we now know how to spot stellar destructions so extreme that they reveal properties of the black hole itself. What happens when a star gets a little too close to a galaxy's central supermassive black hole? Well, as it approaches, the gravitational force on the side of the star closer to the black hole gets stronger than the pull on the far side. This gravitational differential results in a tidal force that, from the star's perspective, feels like it's being stretched in the direction of the black hole and compressed in a perpendicular direction. If the star gets within a certain critical distance of the black hole, the tidal radius, the tidal force becomes greater than the force of gravity binding the star together. The star is smeared out in a fluid-like noodly mess in a process called spaghettification. Some of this material gets ejected outwards while more spirals rapidly into the black hole, leading to incredible temperatures before disappearing into the black hole. These tidal disruption events, or TDEs, are so rare that we've never seen one in our own Sag J star black hole, but we've seen around 100 candidate TDEs in distant galaxies. Even from Sag J star, and certainly from other galaxies, a TDE would appear to us as just a flash of light from the galactic center. But fear not, there is a way to get as close as we want to one of these stellar train wrecks, by recreating them in supercomputer simulations. By tuning those simulations to our observations, we're able to study matter moving in the strange warped spacetime around the black hole. And recently, we've even predicted a type of extreme tidal disruption event never before seen that we may see very soon. Throwing virtual stars at virtual black holes is actually enormously challenging, and we've only just gotten really good at it. To understand how we do this and why it's so hard, let's start with some of the gravitational physics behind these tidal disruption events. We've been able to simulate motion under gravity for some time now. The Apollo program did the orbital mechanics of its spacecraft on supercomputers with the computing power of a handheld calculator from the 90s. These simulations used Isaac Newton's theory of gravity, calculating the gravitational force between all pairs of objects, seeing how those forces change velocities and how those velocities change positions over small time steps, then repeating over and over. The calculations are quick enough that modern supercomputers can calculate the interactions of millions of objects to simulate entire galaxies or even universes. But Newtonian gravity is only an approximation of how gravity really works, an approximation valid when gravity is weak. That's fine for most of the universe, and even for mild tidal disruption events like the one that may have torn apart a moon to form Saturn's rings. But to properly describe a TDE near a black hole, we need the full theory, and that's Einstein's general theory of relativity. Rather than describing gravity as a force, general relativity, or GR, describes the warping of space and time by massive objects, and explains gravity as the effect of that warping on the motion of objects. Although general relativity is incredibly well tested and certainly correct, it's also notoriously complicated. For one thing, the nice symmetries that lead to clean circular or elliptical orbits in Newtonian gravity no longer apply in regions of space where GR becomes important. As a result, orbits around black holes can be twisted and tangled over themselves, especially around rotating black holes. Within a certain distance from all black holes, there are no stable orbits whatsoever.
This gravitational messiness has implications both for a disrupted star and for the complexity of simulating those disruptions on our computers. For the star itself, it means that within a certain distance, all material must either fall into the black hole or be flung back out. We can't have nice ring systems of stellar material in the region close to the black hole. And the complexity of these orbits makes our simulations much more computationally challenging. In GR, we describe the motion of objects under gravity in terms of geodesics, paths taken under pure gravity. To calculate the motion of an object in such a region, it's not enough to calculate the force at every point. You need to plot out the geodesics. In fact, you need to build a map of the warped spacetime. It gets much harder if you have to consider the star's own effect on that spacetime curvature. But fortunately for these TDEs, the star's mass is so piddling compared to the black hole.
I really hope I get through the race tomorrow morning. It's haunting video as a long-distance runner expresses jitters over competing in a half marathon at Disneyland the next day. I'm marginally worried now. 35-year-old Caleb Graves says he was worried about the scorching heat. I was outside for like 20 minutes walking my dog, just walking around the block. It was hot. That felt fine. And then like 10 minutes after I got back in, I just passed out. Just fell asleep, no control over my body. It was heat exhaustion. On race day, the high was 108 degrees. And when Caleb crossed the finish line, he was clutching his chest in cardiac arrest. Good morning. We are at Disneyland. The Georgetown Law School graduate was a Disney superfan. He ran marathons at both Disneyland and Disney World. This time, the heat was unbearable. Ashley Sheck won the half marathon women's race.
Humidity was definitely one of the highest humidity races I've ever experienced, and it definitely made for a very challenging day out there.
This cardiologist says Caleb Graves' death is a lesson for everyone.
This specific issue probably could have been avoided. When your body is telling you that there is something wrong, it's very important that you listen to it.
I really hope I get through the race tomorrow morning.
An international model, once a finalist in the Miss Switzerland pageant, is strangled to death, dismembered with a jigsaw, and then allegedly pureed in a blender. And prosecutors say they already know who did it, her husband. This is the story of 38-year-old Kristina Jaksimovic and the case against her husband and the father of her two kids. Kristina's story takes us to Switzerland, where she lived and worked as a model and later a coach. In 2003, she won the Miss Northwest Switzerland pageant, and by 2008, she was a finalist in the Miss Switzerland competition. She later founded her own business called Catwalk Coach, where she transitioned to a coaching role and mentored aspiring young models.
My name is Christina, the Catwalk Coach, and I'm preparing Natalie for her big show. Let's start with the first pose. If you want to look confident and sexy, take a step aside, turn, and lean back slightly. If you're wearing a dress, take one step ahead, lean back to highlight your legs.
As her career took off, so too did her personal life, and in 2017, Kristina got married. Her husband is this guy, who's only being identified as Thomas in news outlets. Together, Kristina and Thomas shared two daughters. They lived in Binningen, Switzerland, a relatively small municipality just outside the larger city of Basel. All this is in the northwest corner of Switzerland, not far from the French or German borders. And it was this same location, the family home in Binningen, where Kristina was brutally murdered. Her body was found on February 13th, and right away, Swiss investigators knew her death was grisly. Here's a warning, the next description is pretty graphic. Detectives were able to determine that Kristina had been strangled to death, and after that, her body was dismembered. They say the suspect used multiple items to cut up her body, including a knife, garden shears, and even a jigsaw. If that wasn't enough, the suspect later took pieces of Kristina's body and ground them up with a hand blender. According to court documents, she was pureed, and the remains were left in a chemical solution to dissolve. One day after Kristina's remains were discovered, Thomas was arrested. Right away, he told investigators an interesting story, that he found Kristina dead in their home back in January and then panicked. Instead of calling police, he said he decided to cut up the body in her laundry room. It's important to note that both medical investigators and crime scene techs determined that the facts in Thomas's confession didn't quite add up, but that was just his initial story. In March, Thomas changed his tune, saying he killed Kristina, but it was out of self-defense because she was coming at him and he feared for his life. Thomas says Kristina had previously attacked him with a knife, but others say it was Thomas who had a history of attacking Kristina. As investigators dug more into the couple's past, witnesses revealed they'd seen Thomas violently push Kristina up against a wall, holding her by her neck. He'd apparently strangled her in the past too. So Thomas has been in custody since his arrest, but he did appeal for release just this Wednesday. A federal court later denied that request. But during the court hearing, we learn more gruesome details about Christina's murder and Thomas's state of mind. Officials say he showed a, quote, noticeably high level of criminal energy, lack of empathy, and cold-bloodedness after killing his wife. They also said he showed a, quote, conspicuously high level of criminal energy in an assessment, but also that there are concrete indications of mental illness. There are so many layers to this disturbing case, so we sat down with attorney Jennifer Roman to try and make sense of the crime. We know that the victim here, Christina, had been strangled, and just that alone is terrifying and disturbing, and the fact that it's such an intimate way to die, it doesn't happen instantaneously. Does that add at all to the defendant in this case, the fact that he chose to strangle rather than shoot or stab?
This is a very intimate crime. And to the extent that the defendant is going to be claiming maybe not guilty by reason of insanity or try to allege that he had some mental health issues that might mitigate
Welcome to our captivating journey into the world of black body radiation, where we will explore the failure of classical physics. A body that can absorb light of all frequencies falling on it and emits radiations of all wavelengths when heated is called a black body. The emitted electromagnetic radiation is known as black body radiation. In real world, a cylindrical object, hollow and painted black from inside, with a small hole, acts as a black body. Experimental observations have revealed that at a specific temperature, a black body radiates more energy at a particular wavelength than others. This wavelength with maximum energy is known as the peak wavelength. As the temperature of a black body increases, it radiates more energy, and the peak wavelength shifts towards shorter wavelengths. Fascinatingly, black body radiation does not depend on the material or chemical composition of the black body. Regardless of the material, a black body emits the same spectrum at a given temperature. Classical physics attempted to predict the distribution of energy among all possible wavelengths emitted by a black body at a specific temperature. The challenge was to find a formula or equation that accurately represent the relationship between the energy emitted at different wavelengths and the temperature of the black body. According to classical physics, a body is made up of countless atoms. Each atom acts as an oscillator, vibrating with its own frequency and amplitude, thereby emitting light of corresponding frequency. Since a body is made up of countless oscillators, it emits radiation of all possible frequencies, ranging from very few vibrations per second to a significantly high number of vibrations per second. According to classical physics, the temperature of a black body can be varied continuously. It can take on any value, smoothly changing from one value to another. Energy and frequency of the oscillators within the walls of a black body depends primarily on the temperature of the black body. In classical physics, it was believed that the energy and frequency of these oscillators were continuous and could change smoothly with temperature. With increasing temperature of the black body, the oscillators were expected to vibrate with higher energies and frequencies. Therefore, all frequencies and energies of the emitted wavelengths were considered possible, allowing them to take any value, leading to the prediction of no upper limit on the energy or intensity of light produced by oscillators vibrating at high frequencies or shorter wavelengths. However, these classical predictions clashed with experimental observations, leading to a major problem known as the ultraviolet catastrophe, where classical physics predicted an infinite energy output at shorter wavelengths. The word ultraviolet refers to the fact that the problem appeared in the ultraviolet region of the electromagnetic spectrum. This failure of classical physics to fully explain black body radiation challenged the foundations of the field. In our next video, we will delve deeper into the birth of quantum mechanics and a revolutionary new understanding of black body radiation. Thank you for watching.